Every second, the universe reveals secrets that challenge our understanding of existence itself. From breathtaking galaxies shimmering with countless stars to mysterious phenomena that leave even the brightest minds puzzled, the cosmos is a treasure trove of enigmas waiting to be explored. Join us today as we delve into some of the biggest mysteries within the universe. The universe is a vast and mysterious place, filled with celestial objects that both astonish and challenge our understanding of the cosmos. One of the most unusual types of objects discovered is the neutron star. These incredibly dense remnants of supernova explosions contain the mass of about 2 sun-like stars, but are only about 20 kilometers wide. Just a teaspoon of neutron star material would weigh as much as an elephant here on Earth. These stars can spin at astonishing rates, sometimes completing a rotation every few milliseconds, and they often emit beams of radiation that sweep across space like a lighthouse, creating what we know as pulsars. Another fascinating celestial object is a rogue planet. Unlike typical planets that orbit stars, rogue planets wander through space without a solar system. Estimates suggest that there could be billions of these solitary wanderers in our galaxy alone. Some scientists hypothesize that they may have formed around stars before being ejected due to gravitational interactions. The existence of these planets challenges our understanding of planetary formation and dynamics, illustrating just how intricate and unpredictable cosmic processes can be. Black holes are perhaps the most enigmatic objects in the universe. These regions of space have gravitational pulls so intense that nothing, not even light, can escape them. While we cannot see black holes directly, we infer their presence by observing the behavior of nearby stars and gas clouds. An incredible discovery is that of supermassive black holes, which reside at the centers of most galaxies, including our own Milky Way. These giants can contain the mass of millions or even billions of suns and affect the formation and evolution of their host galaxies. Finally, we have the phenomenon of dark matter. Although not a celestial object per se, its presence is felt throughout the universe. Comprising about 27% of the cosmos, dark matter affects the motion of galaxies and galaxy clusters, yet it does not emit, absorb, or reflect light, making it undetectable by traditional means. This mysterious substance has led scientists on a quest to uncover its secrets, making it one of the most intriguing puzzles in contemporary astrophysics. Each of these unusual objects and phenomena offers a glimpse into the extraordinary fabric of the universe and continues to fuel our curiosity about what lies beyond our home planet. Neutron stars and black holes are both the remnants of massive stars, but they differ fundamentally in their physical characteristics and the phenomena surrounding them. When a massive star exhausts its nuclear fuel, it undergoes a supernova explosion, leaving behind a core. If this core is between about 1.4 and 3 times the mass of our Sun, it becomes a neutron star. Neutron stars are incredibly dense, so much so that a sugar cube-sized amount of neutron star material would weigh about the same as an entire mountain. They are primarily composed of neutron particles, which are tightly packed together, resulting in strong gravitational and electromagnetic fields. Black holes, on the other hand, occur when a star's core collapses under its own gravity, surpassing a critical mass threshold. This creates an object with gravity so strong that nothing, not even light, can escape its pull. The boundary surrounding a black hole is called the event horizon. Inside this boundary, the laws of physics as we know them begin to break down. While we can observe the effects of black holes, such as the acceleration of nearby material and the emission of X-rays, black holes themselves remain invisible to direct observation. Surrounding neutron stars, we often find pulsar activity. Pulsars are a type of neutron star that emits beams of radiation from their magnetic poles. As these stars rotate, the beams sweep across space, creating regular pulses, similar to a cosmic lighthouse. This phenomenon allows astronomers to detect pulsars by their periodic signals. Neutron stars can also form binary systems with companion stars, creating dynamic interactions that can result in the emission of powerful jets and X-rays. In contrast, black holes can create incredibly energetic jets as well. particularly in the vicinity of supermassive black holes found in the centers of galaxies. Material that gets too close forms an accretion disk, an elongated region of gas and dust that spirals inwards, heating up to extreme temperatures and producing brilliant emissions across the electromagnetic spectrum. This cosmic dance of matter and energy reveals the fascinating and extreme conditions that exist around both neutron stars and black holes, highlighting their roles as some of the universe's most intriguing objects. Quasars, or quasi-stellar objects, are incredibly luminous celestial entities found at the far reaches of the universe. They were first identified in the 1960s and initially appeared as stars due to their bright light, but further study revealed that they are actually among the most energetic objects in the cosmos. This brilliance stems from supermassive black holes located at the centers of distant galaxies, surrounded by swirling disks of gas and dust, which feed into the black hole. As the material spirals inwards, it accelerates and forms an accretion disk, producing vast amounts of energy, often outshining entire galaxies. One of the reasons quasars are considered such powerful energy sources is the process of converting gravitational energy into light. When gas and dust fall towards the black hole, the immense gravitational forces create high temperatures that cause this material to glow brilliantly across the electromagnetic spectrum. This includes visible light, ultraviolet light, and radio waves. In fact, some quasars emit more energy than all the stars in their host galaxies combined, making them visible from billions of light-years away. Quasars also serve as significant tools for understanding the universe. They act like cosmic beacons, helping astronomers gauge the expansion of the universe and the distribution of matter in the vast empty spaces between galaxies. By studying the light from quasars, scientists have been able to learn about the composition and behavior of intergalactic matter, as well as the conditions that existed in the early universe. Finally, quasars remind us of the dynamic and ever-changing nature of the cosmos. They are not static phenomena. Some exhibit significant variations in brightness over short periods, which hints at the chaotic and dramatic environment surrounding supermassive black holes. Each quasar is a testament to the incredible forces at work in our universe, showcasing the fascinating interplay between gravity, light, and cosmic evolution. Exoplanets, which are planets located outside our solar system, pique the curiosity of scientists and space enthusiasts alike, especially those that reside in the habitable zone of their stars. This zone, often referred to as the Goldilocks zone, is the region around a star where conditions are just right for liquid water to exist on a planet's surface. The presence of liquid water is crucial, as it is a key ingredient for life as we know it. The characteristics of these exoplanets can vary widely, but they share some common traits. They orbit their stars at just the right distances to maintain temperatures where water can remain in liquid form. Additionally, many of these planets possess atmospheres, which can protect surface environments from harmful radiation and regulate temperatures. Some might even have geological features similar to Earth, such as mountains, valleys, and potential signs of past or current water flow. Significantly, the search for exoplanets in the habitable zone is central to our exploration of life beyond Earth. Finding a planet within this zone raises the tantalizing possibility that it could harbor life. Astronomers often focus on stars similar to our Sun, as these are likely to host planets with conditions comparable to those of our own. The discovery of such planets like Proxima Centauri b, located only 4 light-years away, fuels interest in space exploration and the potential for future missions aimed at uncovering signs of extraterrestrial life. Studying exoplanets in the habitable zone not only enhances our understanding of the universe, but also offers insight into the origins of life on Earth. By examining these distant worlds, we can glean information about atmospheric composition, surface conditions, and even the potential for life. As technology advances, the search for these intriguing planets continues, igniting imaginations and sparking hope that we may one day find neighbors among the stars. Gas giants like Jupiter and Saturn present an astonishing array of features that distinguish them from terrestrial planets such as Earth and Mars. Firstly, their massive size is striking. Both of these gas giants are colossal, with Jupiter being the largest planet in our solar system, towering over Earth with a diameter that is more than 11 times greater. Saturn, while slightly smaller, is still an enormous presence with its iconic rings, making it a marvel to observe. Their sheer scale not only sets them apart, but also influences their unique atmospheric conditions. Another compelling characteristic of gas giants is their composition. Unlike terrestrial planets, which are primarily made of rock and metal, Jupiter and Saturn are predominantly composed of hydrogen and helium. In fact, they possess thick atmospheres that extend deep into their interiors. As one descends into their clouds, temperatures and pressures escalate dramatically, leading to fascinating phenomena like metallic hydrogen on Jupiter and gigantic storms that can rage for hundreds of years. The most famous of these storms is the Great Red Spot, a colossal hurricane that is larger than Earth itself. The presence of rings is another intriguing feature that distinguishes Saturn from the terrestrial planets. While Jupiter, Uranus, and Neptune also have ring systems, Saturn's rings are the most extensive and bright, composed of ice and rock particles. These rings vary in composition and density, creating a mesmerizing display. Observing them reveals a dynamic environment with gaps and waves caused by the gravitational influence of Saturn's moons, showcasing the intricate dance between celestial bodies. Finally, the multitude of moons surrounding these gas giants adds to their intrigue. Jupiter alone has over 60 confirmed moons, including the largest moon in the solar system, Ganymede, which even surpasses the planet Mercury in size. Saturn boasts its own impressive suite of moons, with Titan standing out due to its thick atmosphere and surface lakes of liquid methane. These moons present a variety of environments and conditions, offering scientists a wealth of opportunities to study processes that may resemble those of early Earth, or even harbor the potential for life beyond our planet. In exploring these features, we not only gain insight into the nature of our solar system, but also enhance our understanding of planetary formation and evolution across the cosmos. Comets are fascinating celestial objects, often described as dirty snowballs. They are made primarily of ice, dust, and various organic compounds. This unique composition plays a crucial role in determining how a comet behaves as it approaches the Sun. As a comet travels inward from the dark, cold reaches of space, the increasing heat from the Sun causes the ices within it to sublimate, turning directly from solid to gas. This process releases gas and dust particles, creating a glowing cloud around the nucleus, known as the coma. The tail of a comet is one of its most captivating features and is directly influenced by its composition. As the comet nears the Sun, solar radiation and the solar wind, the stream of charged particles emitted by the Sun, push away the gas and dust particles. Depending on the composition of the comet, different gases may be released, leading to variations in the tail's color and characteristics. The tail usually consists of two parts, a dust tail that follows the comet's orbital path, and a gas tail that points directly away from the Sun, creating a striking visual display. Not all comets behave identically. Their activity and tail formation can differ based on their materials. For instance, comets rich in volatile compounds might exhibit more vibrant tails and higher levels of activity. On the other hand, those that have a higher proportion of rock and less ice may produce weaker tails. This variance contributes to the diverse appearances of comets, making each encounter unique and intriguing. As comets move closer to the Sun, their behavior often becomes more chaotic and unpredictable. They can fragment into smaller pieces or even completely disintegrate, depending on their structural integrity and the intensity of solar heat. Each one provides a glimpse into the primordial material that formed our solar system, allowing scientists to understand better the conditions of our early cosmic neighborhood, while continuing to inspire wonder with their spectacular displays. The discovery of rogue planets is a fascinating development in our understanding of the universe. These elusive worlds, which drift through the cosmos without being tethered to any star, challenge many long-held assumptions about planetary formation and stability. Historically, we assumed that planets only formed within the gravitational embrace of their host stars, where they could accumulate materials and share a system with other celestial bodies. The existence of rogue planets suggests that the universe is far more dynamic and diverse than we previously thought. One of the most exciting aspects of rogue planets is their sheer number. Scientists estimate that there could be billions of these lonely wanderers in our galaxy alone, possibly even outnumbering the stars. This raises intriguing questions about how many more planets might exist hidden in the fabric of space that we can't see. These planets could have formed around stars before being gravitationally ejected through various processes, such as gravitational encounters with larger bodies. Their presence hints at a wild past for many star systems, as planets that once belonged to families can become solitary adventurers. Not only does the existence of rogue planets expand our conceptual framework of planetary systems, but it also opens up new avenues for exploration and curiosity. Scientists are examining whether these planets could support life, even in the absence of a star. As unlikely as it seems, it is possible that rogue planets could retain heat from radioactive decay or possess subsurface oceans, which might provide a hospitable environment for microbial life. Such possibilities encourage us to rethink the conditions that could potentially foster life beyond the traditional confines of habitable zones around stars. Ultimately, the study of rogue planets serves as a reminder of our universe's complexity and the many mysteries that still lie ahead of us. Each discovery, such as these wayward orbs, adds a layer to our cosmic story, inviting us to reconsider what we know and to explore the implications of planets drifting through the vastness of space. The journey of these planets, roaming freely through the galaxy, prompts us to ponder our own place in the universe. Spiral galaxies are among the most visually stunning structures in the universe. They are characterized by their distinctive spiral arms that radiate from a central galactic bulge. These arms are often composed of younger stars, gas, and dust, giving them a bright and colorful appearance. The central bulge, which houses older stars, is typically a yellowish hue and can contain a supermassive black hole at its core. The overall structure is bound together by gravity, creating a disk shape that can be quite flat. In contrast, elliptical galaxies lack this spiral structure and often present a more rounded, three-dimensional appearance. They can range from nearly spherical to elongated shapes and are primarily composed of older stars, which contributes to their generally reddish color. The gas and dust that are abundant in spiral galaxies are largely absent in ellipticals, resulting in a different process of star formation. This means that elliptical galaxies evolve more slowly over time, as they do not have the raw materials needed to create new stars. Another difference lies in their stellar populations. Spiral galaxies tend to have a mix of stars at various stages of life, from young blue stars in the arms to older ones in the bulge. Elliptical galaxies, however, are populated mostly by older stars, leading to a more homogeneous appearance. This difference is indicative of their distinct histories. Spiral galaxies are often associated with ongoing star formation, while elliptical galaxies have typically exhausted their star-forming material. Finally, the behavior and dynamics of these galaxies also differ significantly. The rotation of spiral galaxies is evident as their arms create a swirling motion. In elliptical galaxies, the motion of stars is more random. This randomness can lead to collisions and interactions that might not occur in the orderly rotation of spiral galaxies. Understanding these characteristics helps astronomers piece together the evolution of galaxies, shedding light on the vast and complex history of our universe. The Milky Way, our home galaxy, is a striking example of the dynamic processes that shape galactic evolution. Its formation began over 13 billion years ago, originating from a massive cloud of gas and dust within the early universe. Under the influence of gravity, these materials began to clump together, forming the first stars. Over time, these stars created clusters, which merged and evolved into the rich structure we recognize today, filled with stars, planets, and various celestial phenomena. As the Milky Way grew, it accumulated mass through a mechanism known as hierarchical merging. This means it formed through the gradual merging of smaller galaxies and dark matter halos. It is thought that this process contributed to the formation of the galactic disk, where we find the bright spiral arms teeming with young stars. The core of the Milky Way likely holds a supermassive black hole, a common feature for large galaxies, acting as both a giant anchor and a source of fascinating astronomical phenomena. In the grand tapestry of the universe, the Milky Way is not alone. It exists within a group of galaxies known as the Local Group, which includes more than 50 galaxies. Among them, the Andromeda Galaxy is the largest and, like the Milky Way, is a spiral galaxy. The Local Group encompasses a fascinating mix of galaxy types, from dwarf galaxies to larger spirals. The gravitational pull between these galaxies affects their shapes, movements, and interactions, creating a dynamic environment that reveals the intricate nature of cosmic relationships. Interestingly, the future of the Milky Way is intertwined with that of Andromeda. In about 4 billion years, current models suggest that these two galaxies will collide. This event will trigger a spectacular transformation as they merge to form a new galaxy, likely reshaping the structure and star distribution of both. The dance of the Milky Way and its neighbors illustrates not only the past and present dynamics of our cosmic neighborhood, but also hints at the spectacular changes yet to come in the universe. Dark matter remains one of the most tantalizing mysteries in astrophysics. Comprising about 27% of the universe, it is invisible and interacts only through gravity. This elusive substance does not emit, absorb, or reflect light, making it undetectable with traditional telescopes. Yet its presence is inferred from the gravitational effects it exerts on visible matter, radiation, and the large-scale structure of the universe. One of the most compelling pieces of evidence for dark matter lies in the way galaxies rotate. When astronomers observe spiral galaxies, they notice something puzzling. According to Newtonian physics, the stars at the outer edges of these galaxies should move slower than those closer to the center, where the bulk of the mass resides. However, measurements reveal that stars far from the galactic core travel at remarkably high speeds, suggesting an unseen mass must be influencing them. This discrepancy hints at a significant amount of dark matter surrounding galaxies, extending far beyond what we can detect. Further intrigue arises when we consider galaxy clusters. These massive structures contain hundreds or even thousands of galaxies bound together by gravity. The motion of these galaxies within clusters also points to dark matter. When we calculate how much mass is needed to hold these clusters together based on their visible components, the numbers always fall short. Observations of mass through gravitational lensing, where light from distant objects bends around a massive object, provide a clearer picture, revealing that a considerable amount of unseen mass attributed to dark matter is necessary to account for the gravitational pull in these systems. The influence of dark matter extends to the very formation of galaxies themselves. Studies suggest that dark matter acted as a framework in which ordinary matter clumped together to form stars and galaxies. Fascinatingly, without dark matter, galaxies might not have formed at all, as the necessary gravitational forces to bring matter together would have been insufficient. This interplay not only impacts the structure and movement of galaxies, but also shapes our understanding of the universe's evolution, making dark matter a central theme in the ongoing quest to unlock the secrets of our cosmos. When galaxies collide, they create a stunningly chaotic yet fascinating environment. Picture two immense collections of stars, gas, and dust swirling together under the force of gravity. As they begin to interact, their gravitational fields tug at one another, distorting their shapes and triggering a series of events that can ignite the birth of new stars. Among the debris and gas that get compressed during these collisions, areas of high density form. These dense regions are crucial because they provide the right conditions for star formation to take place. As gas clouds become increasingly compact, they cool down, and under the right circumstances, they start to collapse under their own gravity. When the temperature and pressure inside these collapsing clouds reach a certain threshold, nuclear fusion ignites, resulting in the birth of new stars. The visual spectacle of a merging galaxy is breathtaking. Astronomers often capture images of these colliding galaxies, revealing sweeping tales of stars and gas that stretch across the cosmos. Bright bursts of light can often be detected, signaling the formation of new stars as the vast clouds of gas ignite in a radiant display. This process, known as starburst activity, can lead to the creation of hundreds, sometimes thousands of stars within just a few million years. Interestingly, while it seems catastrophic on a grand scale, the result of such cosmic collisions is largely constructive. Many new stars form from the merging materials, enriching the galaxies over time. This cycle of collision, formation, and evolution illustrates the dynamic nature of our universe, teaching us that destruction can also pave the way for creativity and new beginnings among the stars. Irregular galaxies are fascinating celestial objects that stand apart from the more familiar spiral and elliptical galaxies. They tend to lack a distinct shape, which is one of their defining characteristics. Instead, you might observe a chaotic arrangement of stars, gas, and dust, often with young, bright stars scattered throughout. This lack of structure is typically a result of gravitational interactions with other galaxies, which can distort their shape over time. One of the most intriguing features of irregular galaxies is their rich star formation activity. Many of these galaxies are home to a plethora of young, hot stars, suggesting that they are actively creating new stars at a rate that outpaces some of their more orderly counterparts. This vigorous star production can provide astronomers with valuable insight into the conditions and processes that lead to star formation in the universe, particularly in regions that are less influenced by the gravitational pull of neighboring galaxies. Irregular galaxies can also serve as windows into the early stages of galaxy development. Since they often do not possess the stable structures found in older galaxies, they are thought to represent a more primordial state of galactic evolution. Investigating these galaxies helps scientists understand how galaxies form and evolve over billions of years. It's like catching a glimpse of a work in progress. Each irregular galaxy tells a story about the complex interplay of forces at play in the cosmos. Moreover, these galaxies can hold clues about the universal history of dark matter and cosmic structures. The dynamic and often unstable nature of irregular galaxies suggests that they may have interacted heavily with their environments, experiences that shape their eventual evolution into more structured forms. Thus, by studying irregular galaxies, we gain insights not only into their unique characteristics, but also into the larger narratives of cosmic history and galactic formation. Satellite galaxies are smaller galaxies that orbit larger galaxies, known as their host galaxies. This dynamic relationship is an intricate dance, influenced by gravity and the distribution of dark matter. As these satellite galaxies move through the gravitational pull of their host, they can experience various interactions that significantly impact both galaxies. One of the most notable effects of these interactions is gravitational stripping. This occurs when the gravitational forces of the host galaxy tug at the satellite, pulling away its stars, gas, and dark matter. Over time, this can lead to a satellite galaxy losing a considerable portion of its mass, altering its structure, and potentially leading to its eventual dissolution. Such interactions provide a fascinating glimpse into the life cycles of galaxies. Another consequence of these interactions can be the triggering of star formation. When a satellite galaxy merges with or passes closely to its host, the gravitational forces can compress gas within the satellite. This compression may ignite new star formation, creating bursts of activity where numerous stars are born in a relatively short time. Therefore, these encounters can refresh galactic ecosystems, sparking new life and changing the cosmic landscape. Additionally, the exchange of materials between galaxies can occur, enriching each other's gas reservoirs. This cosmic recycling can lead to the transfer of elements forged in stars from one galaxy to another, fostering conditions for future generations of stars to emerge. These interactions highlight the interconnected nature of galaxies in our universe, showcasing how each piece plays a vital role in the grand tapestry of cosmic evolution. The multiverse theory is a fascinating concept in cosmology that proposes the existence of multiple, perhaps infinite, universes beyond our own. These universes may have different physical laws, constants, and properties, Imagine our universe as just one bubble in a vast cosmic foam, where each bubble represents a distinct universe, possibly with different versions of reality unfolding within them. This idea challenges our understanding of existence and has sparked the imaginations of scientists and philosophers alike. Supporting evidence for the multiverse theory often comes from the field of quantum mechanics and certain interpretations of cosmic inflation. Quantum mechanics suggests that particles can exist in multiple states at once, leading to the idea that every possible outcome might create a separate universe. Cosmic inflation, a theory that describes the rapid expansion of the universe just after the Big Bang, also lends credibility to the multiverse theory. According to this idea, different regions of space could have inflated at different rates, leading to a patchwork of universes with varied properties. Some regions might be conducive to life, while others might be utterly barren. This scenario aligns with the notion that our universe is just one instance of a much larger and diverse cosmic tapestry. While direct evidence for the multiverse is elusive, its implications ripple through theoretical research. Scientists continue to explore how our understanding of fundamental physics might eventually connect to or reveal the multiverse. Ultimately, the multiverse theory pushes the boundaries of what we know and invites us to ponder questions about our place in the universe and whether other realities as wondrous as our own exist just beyond the horizon of our understanding. String theory is a fascinating and ambitious framework aimed at explaining the fundamental forces of nature, including gravity, electromagnetism, and the nuclear forces. At its core, string theory proposes that the smallest building blocks of the universe are not point-like particles, but rather tiny, vibrating strings. The way these strings vibrate determines the type of particle they represent, much like the different notes produced by a guitar string. This innovative approach suggests a unified description of all particles and forces, positing that they stem from one fundamental entity, the string. One of the most compelling aspects of string theory is its potential to harmonize general relativity, which describes gravity, with quantum mechanics, the theory that governs the subatomic realm. In doing so, string theory not only offers insights into how these forces interact, but also suggests a deeper, interconnected relationship among them. This unification can lead to a more complete understanding of the universe, encompassing everything from the largest galaxies to the tiniest particles. However, string theory is not without its challenges. One of the most significant hurdles is that the theory operates at a scale that is far beyond current experimental capabilities. The strings themselves are theorized to be incredibly small, on the order of 1/10,000,000,000th of a trillionth of a meter, making direct observation practically impossible with today's technology. This lack of empirical evidence raises questions about the validity of string theory, as scientific theories require not just mathematical consistency, but also testable predictions. Furthermore, string theory encompasses a vast landscape of possible solutions, leading to what is known as the landscape problem. This multitude of possible scenarios makes it difficult to predict which specific version of string theory accurately describes our universe. As physicists continue to explore the implications and intricacies of string theory, the hope remains that one day it may offer a comprehensive framework that unites all known forces and particles in a single elegant theory. Until then, it stands as a testament to human curiosity and the unending quest to understand the cosmos. Gravitational waves are ripples in the fabric of space-time caused by some of the most violent and energetic processes in the universe. Imagine a stone dropped into a calm pond. The ripples spread outwards, creating waves across the water's surface. Similarly, gravitational waves are generated when massive objects, like black holes or neutron stars, collide or accelerate, sending out waves that travel at the speed of light. Though Albert Einstein first predicted their existence over a century ago in his theory of general relativity, it took many decades for scientists to confirm them. The groundbreaking aspect of gravitational waves lies in their ability to allow us to observe and study cosmic events that traditional telescopes cannot detect. While telescopes capture light emitted from stars, gravitational waves offer a different perspective, one that reveals the unseen forces and movements of the universe. For instance, when two black holes orbit each other and eventually merge, They produce gravitational waves strong enough to be detected on Earth, even from billions of light years away. This new method of observing the universe opens up a treasure trove of data about highly energetic phenomena and the fundamental laws of physics. In September of 2015, the LIGO Observatory made history by successfully detecting gravitational waves for the first time. This landmark achievement confirmed a key part of Einstein's theory and heralded a new era in astrophysics known as gravitational wave astronomy. The implications are profound. Scientists can now use these tiny ripples, which are much weaker than light, to glean information about the most extreme and enigmatic objects in the cosmos. The discovery also ignites our curiosity about the universe's evolution and provides clues about its underlying structure. Observing gravitational waves helps us study the life cycles of stars, the formation of black holes, and even the early moments of the universe itself. As we continue to refine our technologies and increase our ability to detect these waves, we may uncover answers to some of astronomy's most challenging questions, inching ever closer to understanding the mysteries of our universe. Time dilation is a fascinating concept born from Albert Einstein's theory of general relativity. It describes how time can pass at different rates depending on the strength of gravitational fields. Near a massive object like a black hole, time is affected in profound ways. This occurs because massive objects warp the fabric of space and time around them, creating a scenario where the stronger the gravity, the slower time ticks relative to an observer far away. Imagine a clock positioned close to a black hole, where gravity is extremely powerful. To an observer far away in space, that clock would appear to tick much more slowly than their own. This effect becomes dramatically pronounced as one approaches the event horizon, which is the point of no return for anything that crosses it. The closer one gets to the black hole, the more extreme this time dilation becomes. While someone near the black hole experiences seconds turning to days, their distant counterpart sees a much different timeline unfolding. This brings us to the heart of general relativity, which reshapes our understanding of time and space. Unlike earlier notions that treated time as a constant and universal measure, Einstein demonstrated that time can stretch, compress, and even bend under the influence of gravity. This means that the interplay between mass and the curvature of space not only affects movement and trajectory, but also influences the very flow of time itself. The implications of time dilation are intriguing, especially when we ponder the nature of black holes. When we observe these cosmic giants, we are not merely looking at a gravitational phenomenon, we are witnessing time behaving in ways that challenge our perception of reality. The dance of time and gravity at these extreme scales opens a window to understanding not only black holes, but also the universe's fundamental structure itself. Cosmic inflation is a pivotal concept in cosmology that addresses one of the most perplexing puzzles in our understanding of the universe, its uniformity. This theory suggests that shortly after the Big Bang, the universe underwent an extremely rapid expansion, growing exponentially in a fraction of a second. This brief yet intense inflationary period helps to explain why the universe appears so homogeneous or uniform on a large scale. Before inflation, the universe was thought to be in a hot, dense state. As it expanded during this inflationary phase, regions that were once close enough to communicate thermally were stretched far apart. This rapid stretching explains why, even at vast distances, regions of space share the same temperature and density. It effectively erased any irregularities that might have existed prior to inflation, smoothing out the universe into a nearly even backdrop on the grand scale of space. Furthermore, inflation accounts for the small fluctuations observed in the cosmic microwave background radiation, which is a remnant from the early universe. These tiny variations are crucial because they served as seeds for the formation of all the galaxies and structures we see today. They demonstrate that while the universe is largely uniform, it still possesses the slight irregularities necessary for the clumping of matter, ultimately leading to the rich structure we observe. Overall, cosmic inflation not only provides a framework for understanding the initial conditions of the universe, but also elegantly ties together observed phenomena in cosmology. It illustrates how a seemingly chaotic beginning could evolve into the stable, vast cosmos that we explore and marvel at today. This theory continues to inspire researchers as they unravel the mysteries of our universe's inception. Dark energy is one of the most fascinating and elusive concepts in cosmology. It is believed to make up around 70% of the universe, yet we know very little about it. The discovery of dark energy emerged from observations in the late 90s, when astronomers noticed that the expansion of the universe is not just continuing, but accelerating. This acceleration suggested that some force was pushing galaxies apart at an increasing rate, a mystery that was labeled dark energy. What makes dark energy particularly intriguing is its negative pressure. While ordinary matter and energy attract one another through gravity, dark energy seems to have the opposite effect. It pushes galaxies apart, driving them further away from each other over time. This has significant implications for the ultimate fate of the universe. If dark energy continues to dominate, we could be headed towards a future where galaxies drift away from us, leaving a vast void in the cosmos. This scenario, often referred to as the Big Freeze, suggests that as the universe expands, it will cool dramatically. Eventually, stars will burn out, galaxies will fade, and the universe could become a dark, cold, and lonely place. This concept challenges our understanding of the cosmos and raises profound questions about its nature and potential end. Interestingly, the precise nature of dark energy remains a mystery. Scientists have proposed various theories, from the possibility that it's a constant energy density filling space to dynamic forms that might change over time. Understanding dark energy is essential for unlocking the secrets of the universe, its past, and its ultimate destiny. As research continues, our comprehension of this enigmatic force could revolutionize our grasp of the cosmos and our place within it. Quantum entanglement presents a profound challenge to our conventional ideas about distance and communication. Entanglement occurs when pairs or groups of particles become linked in such a way that the state of one particle instantly influences the state of the other, regardless of how far apart they are. This means that if you measure one particle, you instantaneously know the state of the other particle, even if it is light years away. This phenomenon seems to defy our everyday experiences rooted in the space-time we perceive. Traditionally, we understand information transfer as something that requires a medium and cannot exceed the speed of light. However, entangled particles operate outside this framework. This baffling situation was famously described by physicist Albert Einstein as spooky action at a distance. The implications of this are immense, suggesting that communication between entangled particles happens instantaneously, effectively challenging our understanding of causality and the limits imposed by distance. Furthermore, the mystery of quantum entanglement leads us to reconsider the very fabric of reality itself. If entanglement can be harnessed, it opens up the possibility of advancements, such as quantum computing and quantum cryptography, which rely on these instantaneous connections. Such technologies could revolutionize communication, allowing for systems that are not only faster, but remarkably more secure than anything currently available. Embracing the concept of quantum entanglement encourages us to think about the universe in a less linear way. It nudges us to consider that the connections between particles might transcend conventional boundaries, blurring the lines between space, time, and the very essence of communication. This astonishing interplay reflects the ongoing journey of scientific inquiry, showing us that our universe is far more intricate than we have yet come to understand. Edwin Hubble's discovery in the early 20th century transformed our understanding of the universe. Before his work, the prevailing view was that the cosmos was static, unchanging, and infinite. Hubble, through his observations of distant galaxies, uncovered a startling reality. The universe is expanding. By studying the light emitted by these galaxies, he found that their light shifted toward the red spectrum, a phenomenon known as redshift, which indicated they were moving away from us. This led him to propose that the farther the galaxy is from Earth, the faster it is receding. This revelation was monumental because it suggested that the universe was no longer seen as a fixed entity. Instead, it embraced the concept of dynamic change on a cosmic scale. The idea that galaxies are not stationary but are on an ever-widening journey away from each other provided the first evidence for what would later become known as the Big Bang theory. This theory proposes that the universe began from an incredibly hot and dense point and has been expanding ever since. Hubble's discovery also had philosophical implications. It encouraged scientists and thinkers to reconsider the nature of the universe and our place within it. What we inhabit is not a solitary, isolated space, but a vast, ever-evolving tapestry of galaxies, cosmic structures, and dark spaces. It shifted the focus of cosmology from a static universe to one that involves history, change, and the beginning of all things. In recognition of his contributions, the Hubble Space Telescope was named in his honor, allowing astronomers to delve deeper into the wonders of the universe. As we gaze into the cosmos today, we stand on the shoulders of Hubble and his groundbreaking insights, forever intrigued by the mysteries that still await discovery in our expanding universe. The Chandra X-ray Observatory, launched in 1999, marked a significant advancement in our exploration of high-energy astrophysics. It is specifically designed to study the universe in X-rays, a form of light that humans cannot see but holds immense information about the cosmos. By observing high-energy phenomena such as black holes, supernova remnants, and neutron stars, Chandra has illuminated aspects of the universe that remain hidden in ordinary light. One of its most notable contributions has been the discovery of countless previously unseen objects. For instance, Chandra has provided unprecedented insights into the behavior of black holes. Observations have revealed how they consume nearby matter, emitting powerful jets and X-ray winds. These processes help us understand the extreme physical conditions surrounding these enigmatic bodies and their influence on galaxy formation and evolution. Chandra's observations also shed light on the behavior of dark matter and dark energy, two of the most mysterious components of our universe. By studying the X-ray emissions from galaxy clusters, scientists have been able to map the distribution of dark matter, offering critical clues about its role in cosmic structure formation. This capability enhances our understanding of how galaxies and clusters interact on vast cosmic scales. Moreover, the observatory has played a pivotal role in studying the remnants of supernova explosions, which are essential for distributing elements throughout the universe. By investigating these remnants, Chandra has helped us understand the life cycles of stars and the processes that lead to the creation of heavy elements, underpinning everything from the formation of planets to the materials necessary for life. Through its innovative contributions, the Chandra X-ray Observatory continues to deepen our comprehension of the universe's most energetic phenomena. The Apollo missions, a remarkable series of space expeditions undertaken by NASA, significantly enhanced our understanding of the Moon and paved the way for future space exploration. One of the most significant breakthroughs came from the samples collected during these missions. Astronauts brought back nearly 400 kilograms of lunar rock and soil, which provided invaluable insights into the composition of the Moon. Analyzing these samples allowed scientists to unravel the Moon's geological history, revealing that it likely formed from debris left over after a massive collision between Earth and a Mars-sized body billions of years ago. Apollo also changed our perspective on the lunar surface and its formation processes. Through detailed examinations of the samples and the high-resolution photographs taken during lunar landings, scientists learned about the structure and age of different lunar regions. This information helped confirm theories about planetary formation and evolution within our solar system. Furthermore, the data gathered paved the way for comparative studies with terrestrial rocks, leading to breakthroughs in our understanding of volcanic activity and impact cratering, not only on the Moon, but on other celestial bodies as well. Moreover, the Apollo missions expanded our comprehension of the Moon's environment. The experiments conducted on the surface, such as the deployment of seismometers, allowed scientists to measure moonquakes and uncover details about the Moon's internal structure. These insights indicated that, much like Earth, the Moon has a layered interior, which consists of a crust, mantle, and possibly a small core. This revelation opened up discussions about the geophysical processes that have shaped not only the Moon, but also other bodies in our solar system. Beyond the Moon, the Apollo missions instigated a broader ambition for space exploration. The advanced technologies developed for these missions, including improved spacecraft design, life support systems, and navigation techniques, laid the groundwork for future missions beyond our planet. Because of the know-how gained during Apollo, humanity set its sights on Mars and other destinations, forever changing our understanding of our place in the cosmos and igniting a passion for exploring the final frontier. The Hubble Space Telescope, launched in 1990, revolutionized our understanding of the universe in profound ways. Before Hubble, astronomers relied heavily on ground-based telescopes, which were limited by Earth's atmosphere. This atmospheric interference blurred images and restricted the quality of observations. However, Hubble resides high above the clouds in the vacuum of space, allowing it to capture breathtakingly clear and detailed images of celestial objects. One of Hubble's most significant contributions was its ability to reveal the vast variety of galaxies that populate the universe. With its sharp vision, Hubble provided a stunning glimpse into the different shapes and sizes of galaxies, from spiral and elliptical to irregular forms. This enhanced view challenged previous notions about galaxy formation and evolution, illustrating that the universe is a bustling metropolis of diverse structures, each with its own story to tell. In addition to studying galaxies, Hubble also played a pivotal role in understanding cosmic phenomena such as black holes and nebulae. Its observations have been crucial in determining the rate of expansion of the universe, leading to the profound realization that this expansion is accelerating. This discovery hinted at the mysterious presence of dark energy, a driving force behind the accelerating universe, fundamentally altering our conception of cosmic dynamics. Furthermore, Hubble has captured images of distant galaxies whose light has traveled billions of years to reach us. These observations allow astronomers to look back in time, glimpsing the universe in various stages of its evolution. This perspective has deepened our appreciation of the cosmos, revealing its vastness and complexity, and sparking a greater curiosity about our place within it. The Hubble Space Telescope has not only changed how we see the universe, but it has also inspired generations to explore the mysteries that lie beyond our home planet. The Voyager missions, launched in the late 70s, have profoundly reshaped our understanding of the solar system. Voyager 1 and Voyager 2 were the first spacecraft to venture beyond the familiar planets and explore the outer reaches of our cosmic neighborhood. One of their most remarkable findings came from the detailed photographs and data they collected of Jupiter and Saturn. These missions revealed a wealth of information about their atmospheres, intricate ring systems, and numerous moons, including the striking surface features of Jupiter's moon, Europa, which has since been considered a prime candidate for potential extraterrestrial life. Voyager 2 went on to explore Uranus and Neptune, offering unprecedented insights into these distant planets. We discovered that Uranus has a tilted axis of rotation, which is unique among the planets. This unusual tilt leads to extreme seasonal changes over its long orbital period. Neptune 2 surprised scientists with its dynamic atmosphere and high-speed winds, which are among the fastest in the solar system. These findings challenged previous assumptions about the characteristics of these gaseous giants, providing a deeper understanding of their formation and atmospheric processes. Beyond just planetary discoveries, the Voyager missions significantly expanded our knowledge of the heliosphere, the bubble-like region of space dominated by solar activity. Voyager 1's journey into interstellar space allowed scientists to measure cosmic rays and the interstellar medium, revealing how our solar system interacts with the space beyond it. This groundbreaking work helped to clarify the boundaries of our solar system and provided insights into the nature of interstellar travel and environments, confirming that other star systems must also experience similar physical phenomena. The success of the Voyager missions has not only enhanced our scientific knowledge, but also ignited public interest in space exploration. Their iconic pale blue dot photograph of Earth from millions of miles away encourages a reflective perspective on our planet's place in the vast universe. As we look to the future, the legacy of the Voyager missions continues to inspire new missions, pushing the boundaries of human understanding and exploration beyond the solar system. The discovery of the cosmic microwave background radiation marked a turning point in our understanding of the universe's origins, providing some of the strongest evidence for the Big Bang theory. This radiation is a faint glow that permeates the entire universe and is remarkably uniform, a remnant from a time when the universe was hot and dense. It was first detected in 1965 by Arno Penzias and Robert Wilson, who stumbled upon it while researching radio waves from the Milky Way. What they found was not just noise, but the lingering signature of the early universe. According to the Big Bang theory, the universe began as a hot, dense point approximately 13.8 billion years ago and has been expanding ever since. As the universe expanded, it cooled, allowing particles to combine and form atoms. Around 380,000 years after the Big Bang, these atoms could interact with light, which had previously been trapped by free electrons. This moment, known as recombination, allowed light to travel freely for the first time, creating a snapshot of the universe in its infancy. The cosmic microwave background radiation is essentially that ancient light, now stretched to microwave wavelengths due to the universe's expansion. Its near uniformity across all observations suggests that it emerged from a hot, dense state. Variations in its temperature provide crucial insights into the initial conditions of the universe and the processes that led to the formation of galaxies and large-scale structures. The slight fluctuations observed in this radiation are believed to be the seeds of all the matter in the universe. Scientists regard the cosmic microwave background as a key component of the Big Bang model because it aligns with the predictions made by the theory. Its existence confirms that our universe had a specific beginning and has been evolving since then. As our tools and technologies improve, we continue to explore and measure these cosmic signals, offering deeper insights into the history and fate of the universe and igniting our thirst for understanding the cosmos. The discovery of pulsars marked a remarkable milestone in the field of astrophysics and was made possible largely by advances in radio astronomy. In the late 1960s, a graduate student named Jocelyn Bell Burnell and her advisor, Anthony Hewish, were using a radio telescope in England to study quasars. During their observations, they detected peculiar regular pulses of radio waves coming from a specific region in the sky. Initially, the signals were so regular that they humorously nicknamed them "little green men," suspecting they might be signals from extraterrestrial life. Upon further investigation, these signals turned out to belong to a new type of astronomical object known as a pulsar. Pulsars are rapidly rotating neutron stars that emit beams of radiation from their magnetic poles. Because these beams are highly directional, they can only be detected when they sweep past Earth, much like the beam of a lighthouse. The rhythmic pulsations occur because the neutron star rotates at astonishing speeds, some even completing a full rotation multiple times per second, leading to a consistent and predictable output of radio waves. The implications of pulsar discovery were profound. Not only did it provide evidence for the existence of neutron stars, cementing our understanding of stellar evolution, but pulsars also became invaluable tools in astrophysics. For instance, their incredibly stable rotation allows scientists to use them as cosmic clocks, helping to test theories of gravity and the structure of space-time. Moreover, studying pulsars in binary systems where they orbit another star has opened new avenues for researching gravitational waves, which are ripples in the fabric of space-time caused by massive objects accelerating in space. Radio astronomy was crucial in uncovering pulsars, and by doing so, enhanced our comprehension of the universe. The discovery illustrated the extraordinary life cycles of stars and provided tools that continue to illuminate the intricate nature of our cosmos. As we delve deeper into the mysteries of pulsars, we strengthen our grasp of both the fundamental laws of physics and the vast, dynamic universe that surrounds us. Black holes stand as some of the most fascinating and enigmatic objects in the universe. At their core, black holes are regions of space where gravity is so intense that nothing, not even light, can escape. This occurs when a massive star exhausts its nuclear fuel and collapses under its own weight. The simplest type is a stellar black hole, formed from a single star, but supermassive black holes are much larger and found at the centers of most galaxies, including our Milky Way. Supermassive black holes contain millions, sometimes billions of times the mass of our Sun. Despite their immense size, these colossal entities are shrouded in mystery. One of their key features is their event horizon, the boundary beyond which nothing can return. Inside this point, the gravitational pull is so strong that the laws of physics as we know them begin to break down. Beyond merely being a one-way ticket, black holes can dramatically affect their surroundings, shaping the galaxy itself. Another aspect to consider is how these supermassive black holes grow. They can acquire mass by consuming gas, dust, and even stars that venture too close. This can lead to the formation of an accretion disk, a rotating disk of material that spirals into the black hole, heating up due to friction and emitting energy. This process can create some of the brightest objects in the universe, known as quasars, shining light across vast distances. Their brightness reveals not only the presence of black holes, but also hints at their growth history and the evolution of their host galaxies. Interestingly, the relationship between supermassive black holes and their galaxies is intricate. Research suggests that the mass of a supermassive black hole correlates with the mass of the galaxy's bulge, implying a connection between their development. This interdependence prompts new questions about the life cycle of galaxies, challenging scientists to unpack the complexities of these cosmic giants. As we continue to explore, black holes not only expand our understanding of gravity and space, but also inspire awe in the grand architecture of the universe. Gamma-ray bursts are among the most powerful explosions in the universe, releasing as much energy in a few seconds as our Sun will emit over its entire lifetime. These cosmic events challenge our understanding of stellar processes in profound ways. Traditionally, we have seen stars as relatively stable objects, transitioning through predictable life stages from formation to their ultimate ends, whether that be as a white dwarf, neutron star, or black hole. Yet, gamma-ray bursts occur under conditions we are only beginning to fully comprehend. Most gamma-ray bursts are thought to originate from massive stars that have exhausted their nuclear fuel, leading to a catastrophic collapse. This collapse produces a black hole or neutron star, coupled with jets of highly energetic particles that travel nearly at the speed of light. The surprise comes from the realization that these jets can break through the star's outer layers, resulting in a brilliant burst of gamma rays. This revelation suggests that stellar life cycles are far more complex than previously suspected and involve violent energetic phenomena that can obliterate what we thought we knew. Moreover, the study of gamma-ray bursts has implications beyond individual stars. They offer insights into the conditions of the early universe. These bursts are frequently observed at great distances, suggesting they were more common during the universe's formative years. Understanding their frequency and behavior can help astronomers piece together the history of star formation and evolution across time, giving us a clearer picture of the cosmos. Gamma-ray bursts not only push the boundaries of stellar theory, but also act as cosmic lighthouses. They illuminate processes that govern the life and death of stars, bridging our current knowledge with the mysteries lurking in the night sky. As we continue to study these phenomena, they promise to reshape our understanding of both stellar physics and the universe's grand narrative. Antimatter is a fascinating counterpart to the matter that makes up our everyday world. While ordinary matter consists of protons, neutrons, and electrons, antimatter is formed from antiparticles. These antiparticles are like shadow versions of their matter counterparts, possessing the same mass but with opposite charges. For example, the antiparticle of the electron, known as the positron, carries a positive charge instead of a negative one. When a particle of matter comes into contact with its antimatter twin, they annihilate each other, releasing energy in the process. This characteristic makes antimatter a powerful energy source, albeit one that remains elusive for practical use. One of the great mysteries of antimatter is its scarcity in the universe. According to the prevailing theories of the Big Bang, equal amounts of matter and antimatter should have been produced. However, our observable universe is overwhelmingly dominated by matter, with only trace amounts of antimatter detected. This imbalance raises profound questions. Where did all the antimatter go? Some researchers propose that slight differences in the behavior of matter and antimatter might have played a role in this disappearance, hinting at new physics that challenges our current understanding of the universe. Another intriguing aspect is the potential applications of antimatter. Scientists have hypothesized that it could be harnessed for everything from advanced propulsion systems in space travel to powerful medical imaging techniques. For instance, positron emission tomography, or PET scans, use small amounts of antimatter to create detailed images of processes within the human body. While the production of antimatter is currently an expensive and resource-intensive endeavor, the possibilities it presents continue to inspire researchers. Moreover, the study of antimatter not only seeks to unlock mysteries about the universe's formation and structure, but also hints at undiscovered laws of physics. Researchers explore questions like whether there is a way to produce or detect more antimatter, or what the implications would be if we discovered antimatter regions in the cosmos. As we delve deeper into the cosmos and the nature of reality itself, antimatter stands as a tantalizing frontier, inviting us to explore the fundamental truths of the universe we inhabit. Magnetars are a unique breed of neutron stars, distinguished primarily by their incredibly powerful magnetic fields. While all neutron stars emerge from the remnants of supernova explosions, magnetars take these remnants to an extreme. A typical neutron star's magnetic field is strong, about 1 million times that of Earth, but magnetars boast magnetic fields that can be 1,000 times stronger than that, reaching levels of around 1 quadrillion Gauss. This immense magnetic force leads to a host of extraordinary properties and behaviors. One of the most fascinating features of magnetars is their capacity to release bursts of energy. These bursts can be incredibly intense, often equivalent to the energy emitted by the sun over a period of several years, all occurring in mere seconds. When magnetars undergo these violent outbursts, they can emit not only gamma rays but also X-rays, making them some of the brightest objects in the universe during these events. This energetic output allows astronomers to study them even from vast distances. Additionally, magnetars exhibit an unusual phenomenon known as starquakes. Just as seismic activity occurs on Earth, the intense magnetic stress in the crust of a magnetar can lead to sudden shifts, resulting in quakes that can release immense amounts of energy. These starquakes can also trigger more subtle variations in brightness, complicating their appearance and behavior further, adding to the challenge and intrigue for scientists trying to study these cosmic phenomena. Magnetars stand out as extraordinary stellar objects, with magnetic fields so strong they defy our conventional understanding of physics. Their energetic bursts, profound magnetic influence, and the dramatic starquakes they produce tell us much about the fundamental workings of the cosmos. As researchers delve deeper into their mysteries, magnetars continue to enrich our understanding of the universe's more exotic inhabitants. The Fermi paradox presents a tantalizing question that has puzzled scientists and astronomers for decades. Named after the physicist Enrico Fermi, it essentially asks, with billions of stars in our galaxy and potentially even more planets, where is everybody? Given the vastness of the universe and the likelihood of habitable worlds, the paradox highlights the stark contrast between the high probability of extraterrestrial civilizations and the conspicuous lack of evidence for their existence. Several theories have emerged in an attempt to explain this mystery. One explanation is the rare Earth hypothesis, which suggests that while simple life forms might be common across the universe, the specific conditions that foster complex civilizations are exceedingly rare. Factors such as a stable planet, appropriate atmosphere, and protective features like a large moon or a gas giant nearby could limit the emergence of intelligent life. This means that Earth might be something of an anomaly, with its blend of circumstances leading to advanced beings. Another intriguing theory is the Great Filter, which posits that there may be some stage in the evolution of life that is incredibly unlikely to be surpassed. This filter could occur either before or after the development of intelligent civilizations. If it's located before, it would mean that many species fail to evolve beyond a simple organism. Conversely, if it's located after, it raises a more chilling prospect. Intelligent civilizations may frequently self-destruct through war, environmental catastrophe, or technological mishaps, preventing them from reaching out to or eventually discovering one another. Lastly, some have proposed the idea of the zoo hypothesis. This perspective suggests that advanced extraterrestrial civilizations are aware of humanity but choose not to make contact, much like zookeepers observing animals in a habitat. Perhaps they are studying us from a distance, allowing us to develop naturally without interference. This raises fascinating questions about the nature of intelligence and the ethical dilemmas of contact. The Fermi paradox remains not just a scientific question, but an invitation to ponder our place in the cosmos and the possibilities that lie beyond our understanding. Cosmic rays are high-energy particles that come from outer space and continually bombard Earth. These particles include protons, electrons, and atomic nuclei, some moving at nearly the speed of light. When scientists capture and study cosmic rays, they unlock valuable information about the universe and the processes generating these high-energy phenomena. By analyzing the composition and energy of cosmic rays, researchers can track their origins and better understand the environments that create them. One of the key insights from cosmic rays is their connection to supernovas, black holes, and neutron stars. These explosive events and dense stellar remnants serve as powerful accelerators, propelling particles to extreme speeds. As cosmic rays pass through the Earth's atmosphere, they collide with air molecules, producing secondary particles. By detecting these secondary particles with ground-based observatories, scientists can trace back the cosmic rays to their potential sources and determine the conditions that enable such immense energy production. Furthermore, studying cosmic rays provides a window into the fundamental nature of matter and energy in the universe. When these rays interact with other cosmic rays or matter, they can create new particles, some of which may hint at phenomena beyond the standard model of particle physics. For example, researchers have discovered that certain high-energy cosmic rays appear to be linked to distant astrophysical events, exposing a connection between our planet and the farthest reaches of the universe. In addition, cosmic rays can influence the Earth's atmosphere and climate. Their interactions can produce clouds, impacting weather patterns over time. By examining these interactions, scientists gain insights into the potential influences of cosmic forces on terrestrial conditions. Exploring cosmic rays not only enriches our understanding of high-energy particles, but also reveals the interconnectedness of cosmic events and our own planet. Dark matter is one of the universe's biggest mysteries. Though we cannot see it, accounting for about 27% of the universe's total mass energy content, its presence is inferred from gravitational effects on visible matter. For example, galaxies spin at speeds that should cause them to fly apart, yet they hold together, suggesting unseen mass exerting gravitational pull. However, this elusive substance exhibits strange behaviors that challenge our understanding of cosmic structure. One intriguing aspect of dark matter is its apparent clustering. Observations show dark matter tends to clump together, forming significant structures like halos around galaxies. But these halos often create a mismatch with the distribution of visible matter. When examining galaxy clusters, researchers expected that combining the dynamics of visible galaxies with dark matter would result in different behaviors. Instead, dark matter appears to dominate these large-scale structures, complicating our models of how galaxies and clusters interact within the cosmic landscape. Another peculiar behavior is the phenomenon known as dark matter interactions. While dark matter is believed to interact primarily through gravity, some theoretical models suggest it might have other weak interactions yet to be confirmed. Experiments searching for these interactions have yielded inconclusive results, leaving scientists puzzled. If dark matter does have additional interactions beyond gravity, it could mean that our understanding of fundamental physics needs a significant overhaul, affecting everything from particle physics to cosmology. These strange behaviors suggest that our universe is far more complex than we initially thought. As researchers continue to gather more data and test new theories, the quest to unveil the nature of dark matter will not only enhance our understanding of cosmic structure, but might also lead to revolutionary discoveries about the fundamental workings of the universe. With every observation, we inch closer to unraveling the mysteries of dark matter, and each revelation raises even more questions, keeping the field of cosmology vibrant and full of wonder. The Kepler space mission, launched in 2009, was a groundbreaking endeavor aimed at uncovering planets beyond our solar system, known as exoplanets. Its primary objective was to determine how many planets might exist in our galaxy, particularly those that lie within what is termed the habitable zone, the region around a star where conditions might be just right for liquid water to exist. This quest to find Earth-like planets drew the attention of both scientists and the public alike, igniting a sense of wonder about the potential for life beyond our own world. Kepler utilized a sophisticated telescope equipped with a unique photometer that could measure the brightness of stars with exceptional precision. By monitoring over 150,000 stars for slight dips in brightness, week-long flickers produced when a planet transits in front of its host star, Kepler could detect planets even smaller than Earth. As a result, the mission discovered thousands of exoplanets, including a significant number in the habitable zone, thus suggesting that planets similar to our own could be common in the cosmos. In addition to simply counting planets, Kepler also provided invaluable insights into the diversity of planetary systems. It revolutionized our understanding by revealing that many stars host multiple planets of varying types, ranging from gas giants larger than Jupiter to rocky planets akin to Earth. This wealth of data has helped astronomers categorize exoplanets based on their size, orbit, and potential to support life, allowing scientists to refine their models about how planetary systems form and evolve. Ultimately, the Kepler mission laid the groundwork for future explorations of exoplanets, sparking new interest in studying their atmospheres, compositions, and potential habitability. By expanding our knowledge and fueling curiosity about the universe, Kepler has sparked an ongoing dialogue about the existence of extraterrestrial life, reminding us just how much we have yet to learn about our place in the cosmos. Scientists have made remarkable discoveries about Mars thanks to the various rovers and landers that have explored its surface. Since the first successful landing of a rover, the scientific community has focused on uncovering the planet's secrets, and each mission has contributed to our growing understanding of its conditions, history, and potential for past life. One of the most significant findings is the presence of water in various forms. Through the analysis of soil and rock samples, researchers have confirmed that water once flowed on the surface, and ice is present at the poles and beneath the surface. The rovers such as Spirit, Opportunity, Curiosity, and Perseverance have provided valuable data about Mars's geology and climate. By examining the layers of rock and sediment, scientists have gathered insights into the planet's volcanic activity and its ancient environments. Curiosity, for example, discovered sedimentary rocks that suggest Mars may have once had conditions suitable for life, resembling those found in some of Earth's most hospitable places. These findings suggest that in its distant past, Mars had a more Earth-like climate, with flowing water and a thicker atmosphere. Additionally, the exploration of Martian soil has revealed essential elements for life, including carbon, nitrogen, and phosphorus. The analysis of these elements offers a glimpse into the potential for past microbial life. The latest rover, Perseverance, is specifically searching for signs of ancient life and collecting samples that may one day be returned to Earth for further study. This mission includes the examination of rocks known to preserve biosignatures, which are clues that might indicate the presence of living organisms. The exploration of Mars does not stop at understanding its past. It also provides insights into its future. With ongoing studies on Martian dust and atmospheric conditions, scientists are unraveling the challenges human explorers may face as we look toward a potential manned mission. The knowledge gained from these robotic explorers is not only piecing together the history of the Red Planet, but also inspiring questions about the possibilities of life beyond Earth and the future of human colonization of our solar system. The New Horizons mission, which flew past Pluto in July 2015, transformed our comprehension of this distant dwarf planet in remarkable ways. Before this mission, Pluto was often portrayed as a cold, desolate world, but the detailed images and data sent back by New Horizons challenged that simplistic view. The spacecraft provided unprecedented close-up photographs and measurements, revealing a dynamic landscape filled with mountains made of ice, vast plains, and even possible indications of atmospheric activity. One of the most striking discoveries was the presence of a large heart-shaped region, informally known as Sputnik Planitia. This area, composed largely of nitrogen ice, is thought to be part of a vast glacial system, suggesting that Pluto is far from inert. The varied terrains showcase a rich geological history, indicating that there have been processes at work that have shaped its surface over time. Scientists also found towering ice mountains reaching heights similar to those of the Rockies, a surprise considering Pluto's small size and distance from the Sun. Additionally, New Horizons revealed that Pluto possesses a thin atmosphere composed mainly of nitrogen, with traces of methane and carbon monoxide. This atmosphere varies in density depending on Pluto's position in its highly elliptical orbit. In fact, as Pluto approaches the Sun, its atmosphere expands, leading to the curious dynamic where atmospheric conditions can change dramatically over time. These features underscore the complexity of Pluto, making it clear that it has a nuanced and active environment. The mission not only reshaped our view of Pluto, but also reignited interest in Kuiper Belt objects more broadly. New Horizons serves as a reminder that even distant and seemingly isolated celestial bodies can hold secrets that deepen our understanding of planetary science and the formation of our solar system. It confirmed that our quest for knowledge about the universe is far from over. In fact, it seems just to be beginning. The Cassini mission, which orbited Saturn for over a decade, significantly expanded our understanding of the planet and its captivating moons. One of the standout discoveries involved Enceladus, a small but intriguing moon that captured scientists' imaginations. Cassini revealed that Enceladus is not merely an icy world, it harbors a subsurface ocean beneath its frozen surface. This ocean is believed to be in contact with the moon's rocky core, creating conditions that could potentially support life. The mission's most startling revelation came from the plumes of water vapor and ice particles that erupt from Enceladus's south pole. Cassini flew through these geysers and collected samples of the ejected material. Analyzing these samples unveiled the presence of essential ingredients for life, including organic molecules and simple sugars. This finding has fueled exciting debates about whether microbial ecosystems could exist in the ocean beneath Enceladus's icy crust. Equally fascinating was the discovery of hydrothermal activity on the ocean floor. Cassini's data suggested that warm water is interacting with the moon's rocky bottom, analogous to hydrothermal vents on Earth's oceans, which teem with life. This environment might provide the necessary chemical reactions to support microbial life, significantly raising the stakes in our search for extraterrestrial organisms in our solar system. The revelations from Enceladus have redefined our quest to explore other worlds for signs of life. With its dynamic geology, abundant water, and tantalizing hints of habitability, Enceladus stands as one of the most promising candidates among the celestial bodies we continue to study in the grand tapestry of our cosmos. The Cassini mission has undeniably opened up a new chapter in our understanding of what might exist beyond Earth. The James Webb Space Telescope, often referred to as JWST, represents a monumental leap in our ability to observe the cosmos, particularly distant galaxies. Launched at the end of 2021, JWST operates in the infrared spectrum, which offers a significant advantage over its predecessor, the Hubble Space Telescope. This is crucial because many of the galaxies we aim to study are located millions or even billions of light-years away. As light travels through expanding space, it shifts to longer wavelengths, a phenomenon known as redshift. The JWST, with its advanced infrared capabilities, allows us to capture this red-shifted light, unveiling details that were previously beyond our reach. The telescope is equipped with an impressive suite of instruments designed to analyze the light from these distant galaxies. Its primary mirror, which spans a massive 21 feet across, gathers light more effectively than any previous man-made instrument. This size enables the telescope to observe fainter objects, leading to discoveries of galaxies that formed shortly after the Big Bang. By peering back in time, scientists can examine the formative years of the universe, resulting in groundbreaking insights into galaxy formation and evolution. Moreover, JWST features a unique cooling system that keeps its instruments at extremely low temperatures, reducing background noise from the telescope itself. This enhancement significantly improves the quality of the data collected. With its exquisite resolution, JWST captures exquisite images and precise measurements of the light from distant galaxies, allowing astronomers to investigate not just their position and shape, but also their composition and the processes occurring within them. Overall, the James Webb Space Telescope doesn't just enhance our observational capacity, it fundamentally reshapes our understanding of the universe. With each image and spectrum returned from its observations, we edge closer to comprehending the vast complexities of cosmic history, from the formation of the first stars to the intricate dance of galaxies in the great tapestry of the cosmos. As we look to the future, JWST promises to be a cornerstone in unraveling the mysteries that lie beyond the stars. The Rosetta mission, launched by the European Space Agency, provided remarkable insights into the nature of comets, revolutionizing our understanding of these icy bodies. One of the mission's major achievements was its detailed study of Comet 67P/Churyumov-Gerasimenko. By deploying the Philae lander to the comet's surface, scientists were able to analyze its composition in ways never before possible. This exploration revealed a wealth of information about the building blocks of the early solar system. One of Rosetta's intriguing findings was the surprising mix of chemicals present on the comet. It was discovered to contain organic compounds, some of which are complex and rich in carbon. This raised fascinating questions about the potential for comets to deliver essential ingredients for life to planets like Earth. With the presence of these organic materials, scientists began to consider how ancient comets could have contributed to the emergence of life by seeding young planets with vital components. Beyond organics, the mission helped researchers understand the physical properties of cometary materials. The comet was found to have a low density, suggesting it is made of a soft, porous mixture of ice, dust, and gas. This composition hinted at a primordial past, as these structures are believed to be remnants from the construction phase of our solar system. The insights gained from Rosetta suggest that comets could serve as time capsules, preserving the ancient materials from which the planets formed. Furthermore, Rosetta observed various phenomena on the comet's surface as it approached the Sun. The mission witnessed dramatic changes in the comet's activity, including the eruption of jets that spewed gas and dust into space. This remarkable behavior highlighted how solar radiation impacts comets, transforming them as they travel through the inner solar system. These findings collectively deepen our understanding of the delicate balance between cosmic processes and the origins of life, reinforcing the idea that comets are more than just wandering icebergs. They are vital historical records of our solar system's infancy. Wormholes are fascinating theoretical constructs in the field of physics, often described as tunnels connecting two separate points in spacetime. Imagine spacetime as a two-dimensional sheet of paper. If you were to fold that paper so that 2 points touch, a wormhole would represent the tunnel that goes through the paper, allowing you to jump from one point to another almost instantly, instead of traveling across the surface. This concept emerges from the equations of general relativity, which suggest that under certain conditions, such shortcuts through the universe might be possible. The idea is that these wormholes connect different regions of space, and potentially even different times. This opens up a wealth of possibilities. For instance, if a person could traverse a wormhole, they might travel vast cosmic distances in a fraction of the time it would normally take. Imagine spacecraft whizzing from Earth to the farthest reaches of our galaxy, or even to other galaxies, in mere moments. In a sense, wormholes could redefine our understanding of travel and exploration in the universe. However, the implications of wormholes stretch beyond just quick travel. They could also lead to profound philosophical questions. If time travel were possible through a wormhole, could someone visit the past or change historical events? Would such actions create paradoxes, or perhaps even alternate timelines? These fascinating prospects keep scientists and philosophers pondering the very nature of time and reality, revealing how interconnected and complex these concepts are. Nevertheless, it's important to remember that wormholes, as we understand them today, remain entirely theoretical. No experimental evidence has confirmed their existence, and creating a stable wormhole would likely require forms of matter or energy that we do not yet comprehend. The fabric of space-time is an intricate and fundamental concept in our understanding of the universe. Imagine it as a vast, four-dimensional tapestry that combines the three dimensions of space with the dimension of time. This fabric is not a simple backdrop, rather, it is dynamic and responsive. When objects with mass, like planets or stars, are present, they cause this fabric to warp and curve around them. This warping is what we perceive as gravity. To illustrate this, picture placing a heavy ball in the center of a trampoline. The fabric of the trampoline bends around the ball, creating a slope. If you roll a smaller ball near the heavy one, it will spiral inward toward the larger mass. In a similar way, smaller objects in space follow paths affected by the curvature of space-time created by larger, more massive objects. This interaction governs the motion of planets, moons, and even light itself. Albert Einstein first introduced this revolutionary idea in his general theory of relativity. He established that gravity is not a force in the traditional sense, but rather a consequence of the geometry of space-time. The more massive an object, the greater the curvature it produces. For example, Earth's gravity pulls everything toward its center, keeping us grounded, while also holding the Moon in orbit, thanks to the way Earth's mass shapes the surrounding space-time. This understanding provides profound implications for our study of the cosmos. It helps explain the orbits of galaxies, the behavior of falling objects, and even leads to predictions about gravitational waves, ripples in space-time produced by violent cosmic events, like the collision of black holes. The fabric of space-time is not just an abstract concept, but a dynamic element woven into the very nature of the universe, influencing the cosmic ballet we observe all around us. Albert Einstein's theories revolutionized our understanding of space and time, particularly through his concepts of special and general relativity. Before Einstein, space and time were seen as separate and absolute entities. However, Einstein proposed that they are intertwined within a single continuum known as space-time. This means that the fabric of the universe is not just a stage where events occur, but a dynamic entity that can warp and bend in response to mass and energy. When applied to astronomical observations, these theories unveil a captivating reality. For instance, light from distant stars and galaxies doesn't travel through an unchanging backdrop. Instead, its path is influenced by the curvature of space-time caused by massive objects like stars and black holes. This gravitational lensing effect allows astronomers to observe phenomena far beyond our immediate reach, revealing the presence of unseen forces and structures in the universe. Moreover, time itself is not uniform. Einstein demonstrated that the closer one is to a massive object, the slower time will pass relative to someone situated farther away. This idea has profound implications in the realm of astronomy. For example, near a supermassive black hole, time dilates significantly. So, while a spaceship might experience time passing normally near a black hole, observers far away would see time moving much faster. These concepts shift our perspective on the universe as a whole. Instead of a fixed panorama of movements and events, we perceive a universe where the interplay of space and time creates a rich tapestry of occurrences, with distances stretching and time flowing unevenly. This realization helps us understand cosmic phenomena, from the bending of light around distant galaxies to the effects of time dilation on satellite navigation, allowing us to appreciate the complexities of the universe in which we exist. Time loops and closed time-like curves are concepts that stretch our understanding of time and causality in ways that can feel both fascinating and perplexing. At the heart of these ideas is the question of whether events can influence themselves, creating a cycle that challenges the traditional linear concept of cause and effect. In the most straightforward scenario, we think of time as a straight line, where one event leads to another in a clear sequence. However, closed time-like curves, as suggested by certain solutions to Einstein's equations of general relativity, propose a more complex framework. Imagine a scenario where a person travels back in time and interacts with their younger self. This interaction raises profound questions. If the person makes a choice that alters their past, how can that choice have already occurred in their timeline? This paradox is known as the grandfather paradox. It illustrates that in a universe with time loops, the chain of cause and effect can become entangled in ways that seem contradictory, blurring the lines of what we perceive as reality. The implications for causality are significant. If we accept the possibility of time loops, we must reconsider the foundational principles of physics that govern our understanding of events. In a traditional perspective, every effect has a distinct cause, but in a model with time loops, an event could become its own cause, challenging our intuitive grasp of how events unfold. This has led physicists and philosophers alike to explore alternative frameworks and theories to reconcile these issues, suggesting a potential need to redefine our understanding of time itself. Ultimately, the exploration of closed time-like curves encourages both scientists and laypeople to think beyond conventional narratives of time. It invites us to ponder the mysterious nature of existence and the interconnectedness of our actions across time. This realm where time may loop back upon itself remains one of the most intriguing areas of modern physics, offering fertile ground for further inquiry into the very nature of reality. The theory of relativity, proposed by Albert Einstein, fundamentally changed our understanding of space, time, and gravity. It presents profound challenges when we seek to connect it with another fundamental pillar of modern physics, quantum mechanics. While relativity governs the macroscopic realm of stars, galaxies, and cosmic phenomena, quantum mechanics delves into the microscopic world of atoms and subatomic particles. The two theories, remarkable in their own rights, operate on vastly different principles, leading to a puzzle that physicists are still eager to solve. One of the main issues arises from their differing views on gravity. In general relativity, gravity is not a traditional force but rather a curvature in the fabric of space-time caused by mass. Massive objects like planets and stars bend space-time around them, influencing the motion of other objects. In contrast, quantum mechanics views forces through the lens of particles, like gravitons, hypothetical particles that would mediate the force of gravity at the quantum level. This fundamental difference complicates our understanding of how gravity works at tiny scales. Another complication is the nature of black holes and singularities. At the center of black holes lies a singularity, a point where current understanding breaks down and gravitational forces are thought to become infinitely strong. Here, the rules of general relativity collide with those of quantum mechanics, leading to a set of paradoxes. For instance, when considering what happens to information that falls into a black hole, traditional notions of quantum information clash with the irreversible nature of gravitational collapse. As physicists explore these complexities, they seek a framework, often referred to as quantum gravity, that could harmonize these two theories. Concepts like string theory and loop quantum gravity are being investigated, each trying to offer insights into a unified model. While a complete reconciliation remains elusive, the ongoing exploration reveals the richness of the universe and the depths of our current knowledge, highlighting that there is still so much more to learn about the nature of reality itself. Studying the atmospheres of distant exoplanets or planets outside our solar system involves a fascinating blend of advanced technology and the principles of astronomy. Scientists primarily use a technique called spectroscopy, which examines the light emitted or absorbed by objects in space. When light from a star passes through the atmosphere of an exoplanet during a transit, or when the planet moves in front of the star, it leaves a unique signature on the light. This signature reveals the chemical composition of the atmosphere, including vital clues about the presence of elements like hydrogen, helium, and even water vapor. Recent breakthroughs in this field have been remarkable. One of the most notable achievements is the detection of atmospheric water vapor on exoplanets, which raises exciting questions about the potential for life beyond Earth. For example, in 2021, the Hubble Space Telescope provided evidence of water vapor in the atmosphere of a nearby exoplanet called WASP 121b. This exoplanet is unique for its extreme conditions, including scorching temperatures that can reach over 2,000 degrees Celsius, allowing for insights into how atmospheres behave under such harsh circumstances. Moreover, the James Webb Space Telescope, launched in late 2021, has dramatically enhanced our ability to study these distant worlds. With its cutting-edge instruments, it can capture even more detailed spectra and detect smaller, fainter signals. For instance, scientists are eager to analyze the atmospheres of rocky planets located in their stars' habitable zones, where conditions might be just right for liquid water, a crucial ingredient for life as we know it. Overall, the exploration of exoplanet atmospheres is still in its infancy, but the progress has been exhilarating. Each discovery unravels more mysteries of the universe, and as we refine our techniques, we edge closer to answering one of humanity's oldest questions. Are we alone in the cosmos? The answers lie out there, waiting to be revealed as we continue to look deeper into the vastness of space. Studying the potential for life on the icy moons of Jupiter and Saturn holds immense significance for our understanding of astrobiology and the conditions that could support life beyond Earth. These moons, particularly Europa, Enceladus, and Titan, present some of the most compelling environments in our solar system where life might exist, despite their extreme conditions. Europa, for instance, is covered by a thick shell of ice, beneath which lies a vast ocean of liquid water. This combination of water and possibly geothermal energy makes it one of the prime candidates in the search for extraterrestrial life. Enceladus, one of Saturn's moons, has shown remarkable signs of activity. It ejects plumes of water vapor into space, indicating that there is not only a subsurface ocean, but also the potential for chemical interactions between water and rock. Such interactions are crucial because they can create an environment rich in organic materials, which are essential for life as we know it. Studying these plumes can provide researchers with direct samples to analyze, potentially revealing the building blocks of life or even signs of microbial organisms. Titan, Saturn's larger moon, offers a different but equally intriguing scenario. It boasts lakes of liquid methane and ethane, presenting an alien chemistry that might support life forms based on entirely different biological principles. This challenges our understanding of what life can be and where it might thrive. Studying these icy worlds expands our perspective on the diversity of habitats that exist in the universe, which in turn influences our own searches for life beyond Earth. The investigation of these moons not only enlightens our quest for understanding life's existence outside our planet, but also enhances our knowledge of planetary processes, climate evolution, and the history of our solar system. Each discovery from these icy moons could potentially rewrite the narrative of life's adaptability, pushing the boundaries of how we conceive life in the cosmos. As our technology advances, the exploration of these fascinating moons promises to yield even more exciting revelations, fueling our curiosity about the universe and our place within it. Terraforming is a fascinating concept that refers to the process of modifying a planet's environment to make it habitable for humans and other earthly life. This idea takes center stage in discussions about colonizing other planets, particularly Mars, as it suggests a pathway to transforming these extraterrestrial locations into Earth-like spaces. Imagine turning a barren, cold landscape into a thriving environment where plants could grow and humans could walk around without the need for bulky spacesuits. At its core, terraforming would involve altering a planet's atmosphere, temperature, and surface. For Mars, that might mean releasing greenhouse gases to warm the planet and thicken its atmosphere, potentially allowing liquid water to flow on the surface. Scientists propose various methods for this, such as using large mirrors in orbit to reflect sunlight, or even introducing specially engineered microorganisms to produce oxygen or modify the soil composition to support life. Each of these ideas presents both technical challenges and ethical considerations. The implications of successful terraforming stretch beyond mere survival. If we could create a habitable environment on another planet, it would open up a vast frontier for humanity. It could ease the pressures on Earth's resources, provide a new backdrop for human exploration, and even allow for the preservation of Earth's biodiversity by creating backups of various species on other worlds. The dream of living on another planet suddenly shifts from science fiction to a tangible goal. However, the journey towards successful terraforming is laden with uncertainties. We still grapple with understanding how ecosystems work and what the long-term impacts of such significant changes might be. The ethical debate around the potential to manipulate other worlds and the responsibility that comes with it can't be overlooked. As exciting as the vision of terraforming is, it leads us to ponder not only how we could change other planets, but also how we should view our relationship with the universe at large. Recent missions to Venus have unveiled some astonishing insights into the planet's geology and climate, illuminating surprising similarities and stark differences between it and Earth. One of the most significant revelations comes from data collected by the Akatsuki orbiter, which has been studying Venus's atmosphere since 2016. The findings show that while both planets are rocky neighbors in our solar system, Venus has a vastly different environment characterized by extreme temperatures and pressures. The surface of Venus is an inhospitable landscape dominated by volcanic plains, with numerous mountains and highland areas. Radar maps produced by missions such as Magellan in the early 1990s and more recent observations have shown numerous volcanic features, suggesting that the planet may still be geologically active today. In contrast, Earth's surface is constantly reshaped by tectonic activity and erosion. This difference highlights how Venus's geology has largely been shaped by its unique atmospheric conditions and a lack of water erosion, leading to its relatively young surface age, which is estimated to be about 300 million years. Climate-wise, Venus presents a striking contrast to the temperate conditions on Earth. With an average surface temperature reaching around 300 degrees Celsius, Venus is the hottest planet in our solar system, primarily due to a thick atmosphere rich in carbon dioxide. This creates a runaway greenhouse effect, trapping heat in a way that hugely elevates temperatures, even more than those found on the much closer Mercury. Earth, on the other hand, maintains a balmy climate owing to its balanced atmospheric composition and the presence of oceans, which regulate temperature. The recent missions have not only shed light on these fundamental differences, but have also pushed scientists to rethink how we classify planets and their atmospheres. The study of Venus is prompting renewed interest in climate dynamics and planetary geology as we grapple with the pressing issue of climate change here on Earth. Understanding the extremes of our neighboring planet might offer critical lessons for managing our own planet's future, making these explorations all the more relevant. The discovery of exoplanets, or planets beyond our solar system, has significantly reshaped our understanding of how planets form. Traditionally, planetary formation theories were largely based on our observations of the 8 planets orbiting the Sun. These theories suggested that planets formed from the dust and gas surrounding young stars, gradually coalescing through a process of accretion. However, the vast array of exoplanets we have observed has revealed that our solar system is just one of many possibilities in the cosmos. Since the first confirmed exoplanet was detected in the mid-1990s, thousands of others have been found, showcasing a remarkable variety of sizes, compositions, and orbital characteristics. Some of these exoplanets are remarkably different from those in our solar system, giant gas planets orbiting very close to their stars, for instance. This phenomenon, known as hot Jupiters, has prompted scientists to reconsider the dynamics of planetary formation and migration, suggesting that planets may not remain in the locations where they originally formed. Additionally, the diversity in planetary systems has led researchers to recognize that various environmental factors, such as the composition of protoplanetary disks and the influence of nearby stars, play a crucial role in shaping how planets form. These insights challenge the once standard model and imply that there may be multiple pathways to creating planetary systems. Consequently, there's been a shift towards developing a more inclusive theoretical framework that accounts for this wide range of planetary characteristics. As we continue to gather more data about exoplanets, especially regarding their atmospheres and potential habitability, our understanding of planetary formation will keep evolving. This exploration not only enhances our appreciation of how planets emerge, but also invites profound questions about the potential for life beyond Earth, making each new discovery an exciting chapter in the story of the universe. The early universe is a fascinating tapestry of events that unfolded in the blink of an eye, yet many aspects remain shrouded in mystery. One of the most enduring puzzles is the phenomenon of cosmic inflation. Just moments after the Big Bang, the universe is believed to have undergone an explosive expansion, growing faster than the speed of light. This begs the question, what triggered this rapid expansion? Understanding the origins of inflation could unlock answers about the overall structure of the universe as we see it today. Another riddle lies in the formation of large-scale structures like galaxies. While we have a good understanding of how matter works under the influence of gravity, the specifics of how clumps of matter coalesced into the vast arrays of galaxies we observe now still eludes us. The early universe was a hot, dense soup of particles, and as it expanded and cooled, fluctuations in density could have led to the formation of the first galaxies. However, the exact processes behind these early gravitational instabilities remain a topic of intense research. Additionally, the nature of dark matter and dark energy presents profound questions about our understanding of the cosmos. Together, these mysterious components make up about 95% of the universe's total energy density, yet their properties are still largely unknown. Scientists speculate that dark matter could have played a critical role in the universe's early evolution by helping to form structures through gravitational attraction. Yet what this dark matter actually is remains one of the most enticing enigmas in modern physics. Lastly, we must consider the asymmetry between matter and antimatter. According to current understanding, the Big Bang should have produced equal amounts of both. Yet, we observe a universe predominantly composed of matter. How did this imbalance arise? This question not only poses fundamental challenges to our understanding of particle physics, but could also reshape our knowledge of the universe's fate. Each of these mysteries invites further inquiry and exploration, reflecting the profound complexities of our early cosmos. Gravitational lensing is a fascinating phenomenon where massive objects like galaxies or clusters of galaxies bend the light from objects behind them. This effect is a direct consequence of Einstein's theory of general relativity, which describes how mass influences the curvature of space and time. When light from a distant star or galaxy passes near one of these massive objects, the path of that light is altered due to the object's gravitational field, creating a lensing effect that can magnify and distort the image of the distant object. Scientists harness this effect to learn more about the universe and its contents. Gravitational lensing helps them discover objects that are otherwise too faint to see. When a distant galaxy's light is bent by a foreground galaxy, astronomers can observe multiple images of the same galaxy, sometimes arranged in beautiful arcs or rings. This not only provides insights into the shape and distribution of the foreground mass, but also offers clues about the distant object itself, allowing researchers to study characteristics like its distance and the materials it contains. Moreover, gravitational lensing plays a crucial role in understanding dark matter. Since dark matter does not emit or absorb light, it is invisible to traditional telescopes. However, its presence can be inferred by observing how it bends light from distant sources. By mapping the degree to which light is distorted, scientists can create a picture of the dark matter's distribution in the foreground mass, offering a glimpse into the unseen components of our universe. This technique has revolutionized modern astronomy and cosmology, allowing us to probe the universe's secrets on large scales. As we learn more about these distant celestial bodies, we gain a better understanding of the cosmos, from the formation of stars and galaxies to the fundamental structure of the universe itself. Gravitational lensing not only opens new doors for exploration, but also deepens our appreciation for the intricate dance of light and gravity that surrounds us. The Great Attractor is a fascinating region in space that has significant implications for our understanding of galaxy clusters. Located in the direction of the Centaurus and Hydra constellations, this gravitational anomaly is pulling a vast number of galaxies towards it, including our own Milky Way. This has led astronomers to rethink how galaxies are structured and how they interact with one another in their cosmic dance. One of the most intriguing aspects of the Great Attractor is its ability to influence the motion of entire galaxy clusters. It suggests that galaxies do not exist in isolation, but are part of a larger web of gravitational forces. The unseen mass of the Great Attractor, which consists of billions of solar masses, indicates that our universe is far more interconnected than previously understood. Observations show that galaxies are moving toward this region at remarkable speeds, which highlights the complex dynamics that govern cosmic structures. Furthermore, the Great Attractor challenges our perception of dark matter. This invisible substance is believed to make up a substantial portion of the universe's mass and is essential for explaining how galaxies cluster and move. Studying the Great Attractor allows scientists to glean insights into the distribution and influence of dark matter in our universe. It modifies our theories about how galaxies form and evolve, pushing scientists to explore new models that account for these gravitational pulls. Lastly, the existence of the Great Attractor invites deeper questions about the large-scale structure of the universe. As we continue to map the cosmos and observe other gravitational influences, we refine our understanding of how cosmic structures come together. Each new discovery in this area provides pieces to the puzzle of cosmic evolution, ultimately enhancing our grasp of the universe and our place within it. The Great Attractor is not just a curious phenomenon, it's a key that unlocks deeper insights into the universe's dynamics. Cosmic strings are fascinating theoretical constructs in the field of cosmology. They are perceived as one-dimensional topological defects that could form during phase transitions in the early universe. Imagine these defects as incredibly thin, yet immensely dense, strands that stretch across vast distances of space. According to current models, they could arise when the temperature of the universe dropped sufficiently for different regions to settle into different states, much like how water freezes into ice at a certain temperature. In the context of cosmic inflation, which suggests a rapid expansion of the universe after the Big Bang, cosmic strings could have formed as the energy densities fluctuated. They are thought to carry immense gravitational effects, manifesting as distortions in the fabric of space-time. Their presence could potentially explain certain cosmic phenomena, such as the distribution of galaxies or the anomalies in cosmic background radiation. These strings could also be remnants of grand unified theories unifying the four fundamental forces of nature. While cosmic strings remain hypothetical, having not yet been directly observed, they provide valuable insights into the interplay of space, time, and gravitational forces. They might even connect with theories that delve into the very large and the very small, bridging our understanding of cosmology and quantum mechanics. The search for cosmic strings could reveal more about the universe's structure and history, shedding light on its early moments right after the Big Bang. Overall, cosmic strings encourage us to ponder the intricate tapestry of the universe, igniting our imagination about the possibilities that lie beyond our current understanding. As researchers continue to explore these possibilities, cosmic strings serve as a reminder of how much we have yet to learn about the cosmos and our place within it. Studying the cosmic web presents numerous challenges, primarily due to its vastness and the complex nature of its structure. The cosmic web is composed of filaments, clusters, and voids, which together make up the large-scale structure of the universe. These features are incredibly diffuse and extend over enormous distances, making them difficult to observe and map accurately. Instruments like telescopes must capture faint light signals from extremely distant galaxies, often obscured by gas and dust in the universe, which adds an additional layer of difficulty. One major challenge is the sheer scale of the cosmic web. It stretches across more than 13 billion light-years, meaning that traditional observational methods can fall short when trying to capture its intricate details. Researchers use advanced simulations and modeling to help predict the distribution and behavior of galaxies within the cosmic web. By comparing these models with observational data, scientists can gain insights into its structure and formation. Despite these challenges, significant discoveries have emerged regarding the cosmic web. For instance, astronomers have learned about the importance of dark matter in shaping the web's structure. Dark matter, which does not emit or absorb light, affects how galaxies are distributed across the cosmic web, illustrating a gravitational framework that holds galaxies and clusters together. This finding has transformed our understanding of the universe, revealing a more intricate interplay between visible and invisible matter. Another fascinating discovery is the realization that galaxies are not randomly distributed in the universe, but rather follow a pattern along the cosmic web's filaments. These filaments serve as highways, guiding the flow of gas and stars, where galaxies form and evolve. By studying the cosmic web, scientists continue to piece together the history of the universe, uncovering not just where galaxies exist, but how they interact and what conditions led to their formation. Each breakthrough deepens our appreciation of the vast cosmic structure that forms the backbone of our universe. The universe is a vast and varied place, filled with environments that push the boundaries of what we consider extreme. One of the most astonishing examples is the surface of Venus, where temperatures soar to around 900 degrees Fahrenheit, significantly hotter than any oven. The thick atmosphere, composed mainly of carbon dioxide with clouds of sulfuric acid, creates crushing pressure more than 90 times that of Earth's atmosphere at sea level. Studying Venus not only helps us understand its inhospitable nature, but also provides insights into the potential for climate change on our own planet. Moving far away from our solar system, we encounter neutron stars, remnants of massive stars that have exploded in supernovae. These stars pack a mass greater than that of our Sun into a sphere only about 12 miles across. The gravity here is unimaginably strong, so intense that a sugar cube-sized amount of neutron star material would weigh about the same as all of humanity combined. Observing these stellar corpses teaches us about the fundamental forces of nature and the very fabric of matter itself, challenging the limits of our current scientific understanding. In contrast, the vacuum of space can be considered an extreme environment too. It is not just the absence of air or matter. The radiation intensity in space, especially from cosmic rays, can be deadly. Yet some microorganisms, like tardigrades, thrive in these conditions. They enter a state of cryptobiosis, practically shutting down their metabolism to survive exposure to extreme levels of radiation, extreme temperatures, and even the vacuum of space. Understanding how these resilient life forms endure such harsh climates can pave the way for advancements in biotechnology and inform future exploration into our solar system and beyond. Lastly, we cannot overlook the possibility of life in extreme environments on other planets and moons. Places like Europa, one of Jupiter's moons, have vast oceans hidden beneath ice crusts. This icy exterior and the potential for life in subsurface oceans offer tantalizing possibilities. By studying these extremes, we gather essential knowledge about the resilience of life, the conditions necessary for habitability, and the myriad ways life might adapt to survive in otherwise hostile conditions. Each extreme environment we uncover adds a piece to the puzzle of our existence and the potential for life beyond Earth. The discovery of Oumuamua in 2017 marked a pivotal moment in our understanding of interstellar objects. This cigar-shaped visitor from another star raised eyebrows among astronomers, not merely because it was the first known interstellar object to pass through our solar system, but also due to its enigmatic nature. The object's unusual shape, rapid speed, and erratic trajectory prompted scientists to reconsider what they thought they knew about celestial bodies beyond our solar neighborhood. Researchers began to study Oumuamua using a combination of telescopic observations and computational models. They analyzed its brightness and colors to glean information about its surface composition and rotation. What they found was astonishing. Unlike typical asteroids or comets from our solar system, Oumuamua's characteristics suggested that it might not fit neatly into any preconceived category of interstellar bodies. Its unexpected acceleration as it skirted the Sun led to speculation that it could be a fragment of a larger object, perhaps even a piece of technology from an advanced civilization. This examination has sparked a series of debates and investigations into other interstellar objects. The anomaly of Oumuamua has led to the development of new observational programs focused on spotting similar visitors. Astronomers are now more eager to detect and classify interstellar objects, enhancing our understanding of the diverse materials and conditions present in the cosmos. This is a critical step in challenging earlier assumptions that interstellar objects should mirror the knowledge we have gathered from comets and asteroids in our solar system. Ultimately, Oumuamua serves as a reminder that the universe is ever full of surprises. Each new discovery encourages scientists to push the boundaries of their understanding and to keep an open mind about the complexities of our cosmic environment. As more interstellar visitors like Oumuamua are detected and studied, we may find that our preconceived notions of celestial bodies need continuous refinement, reflecting the boundless mystery that is the cosmos. Magnetic fields play a subtle yet significant role in the universe, influencing a variety of cosmic phenomena, including the birth of stars. These fields are created by moving electric charges, which means they are inherently linked to the motion of charged particles in space. Magnetic fields are found almost everywhere, from the planets in our solar system to vast clusters of galaxies. They can be surprisingly strong in certain regions, influencing the behavior of gas and dust clouds, the building blocks of stars. One of the most intriguing aspects of magnetic fields is their role in star formation. When giant clouds of gas and dust, known as molecular clouds, begin to collapse under their own gravity, the presence of a magnetic field can provide both support and resistance. On one hand, the magnetic field can help prevent too rapid of a collapse by exerting pressure against the gravitational pull. On the other hand, it can also guide and channel material toward the center of the cloud, facilitating the formation of stars. This tug-of-war between gravity and magnetism is crucial in determining how efficiently stars form in different environments. Moreover, magnetic fields contribute to the dynamics of how stars ignite and evolve. As a star forms, its rotating mass generates and strengthens the magnetic field, which can influence material both inside and outside the star. This interaction has implications for stellar winds, the streams of charged particles released from a star's surface, which can affect the surrounding interstellar medium. Consequently, magnetic fields are not merely passive players, they actively shape the evolution of stars and their environments. In a broader cosmic context, understanding magnetic fields helps astronomers piece together the complex life cycle of galaxies and the universe itself. Since stars are the factories of elements essential for life as we know it, uncovering the mysteries of magnetic fields and their impact on star formation enhances our comprehension of the universe's evolution and the origins of the elements that make up everything around us. As scientists continue to explore these magnetic landscapes, they unlock more secrets of the cosmos, revealing the intricate tapestry that connects stars, galaxies, and ultimately, us. The polar vortexes on gas giants like Neptune have some fascinating differences when compared to those on Earth. One of the most striking distinctions is their size and structure. On Earth, polar vortexes form in a relatively confined area and are often affected by the planet's land and ocean features. In contrast, Neptune's polar vortexes can span vast distances, sometimes extending over thousands of kilometers. This expansive nature allows them to display intricate and stable patterns that are quite different from the more dynamic and variable polar vortices seen on our own planet. Moreover, their formation and maintenance differ significantly due to each planet's atmospheric composition and dynamics. Neptune's atmosphere is primarily composed of hydrogen, helium, and methane, leading to unique interactions and behaviors within its high-speed winds. The winds on Neptune can reach speeds of over 200 meters per second, generating extensive turbulence. This high-energy environment supports the development of long-lasting and extraordinarily structured polar vortexes, which can persist for months or even years. In terms of temperature, the polar vortexes on these gas giants are also much colder. Neptune has average temperatures around -200 degrees Celsius, which contributes to the stability and layered structures observed in its polar regions. These features stand in stark contrast to the comparatively warmer and more unpredictable polar vortexes of Earth, often influenced by seasonal changes and atmospheric conditions. Finally, while we observe seasonal shifts in the polar vortex on Earth, this behavior does not translate directly to gas giants. Neptune's seasons last for decades due to its long orbital period around the Sun. Understanding these polar vortexes on Neptune not only unveils the complexity of its atmospheric phenomena, but also provides insights into the atmospheric dynamics of other gas giants in our solar system and beyond. Lagrange points are unique locations in space where the gravitational forces of two large celestial bodies, like Earth and the Moon or Earth and the Sun, create a balance that allows smaller objects to maintain a stable position relative to the two larger bodies. There are 5 such points, labeled L1 through L5, each with its own characteristics and significance in orbital dynamics. The first 3 Lagrange points, L1, L2, and L3, lie along the line connecting the two large bodies. For example, L1 sits between Earth and the Sun, making it an excellent position for solar observatories as they can continuously face the Sun and avoid the Earth's shadow. L2, located beyond the smaller of the two bodies, provides a clear view of deep space, making it a prime spot for telescopes like the James Webb Space Telescope. L3 is hidden behind the larger body, offering a somewhat isolated vantage point. The remaining 2 points, L4 and L5, form an equilateral triangle with the two large bodies, creating stable locations that benefit from a gravitational tug-of-war between them. These points are especially appealing for missions involving artificial satellites, as they can remain relatively at rest with respect to the Earth and the Moon or the Earth and the Sun. This stability means that spacecraft positioned at L4 or L5 require minimal energy for station keeping, enabling long-term observation missions or relaying communications. Utilizing Lagrange points not only expands our capability to explore and study space, but also enhances our understanding of gravitational dynamics. They open strategic opportunities for deploying satellites, conducting scientific research, and even preparing for future space missions, underscoring the elegance of celestial mechanics and the intricate balances at play in our universe. In the early 1970s, astronomers made a groundbreaking discovery that would significantly enhance our understanding of the universe: the detection of pulsars. These highly magnetized, rotating neutron stars emit beams of radiation that sweep across space. When these beams cross the Earth, they produce regular pulses of radio waves. The first pulsar was discovered by Jocelyn Bell Burnell and Anthony Hewish, marking a revolutionary moment in astrophysics. This finding not only confirmed the existence of neutron stars, but also opened an entirely new window into the cosmos. Detecting pulsars revealed a wealth of information about neutron stars, which are the remnants of massive stars that have exploded in supernova events. Pulsars are incredibly dense, with a mass greater than that of the Sun compressed into a sphere only about 15 miles across. The regularity of their pulse frequencies allowed scientists to study the extreme conditions that characterize these celestial objects. By observing the timing and frequency of pulsar emissions, researchers could infer properties like the star's rotation speed, magnetic field strength, and even its mass. Moreover, the study of pulsars has led to significant advancements in our understanding of gravitational physics. The detection of pulsars in binary systems, where two neutron stars orbit each other, provided a unique laboratory for testing Einstein's theory of general relativity. As these neutron stars orbit, they emit gravitational waves, ripples in spacetime that were predicted by Einstein but only directly detected much later. Observations of these binary pulsars have confirmed many of the predictions of relativity and have also allowed scientists to measure the effects of gravitational wave emissions on their orbital dynamics. The detection of pulsars has been transformative. It has not only deepened our understanding of neutron star properties, but has also reinforced fundamental theories of physics. The intricate dance of light and gravity that pulsars reveal captivates and inspires ongoing research, unlocking the mysteries of the universe one pulse at a time. Spectroscopy has been a pivotal tool in our quest to understand the universe and the composition of celestial bodies. By splitting the light from stars and galaxies into its constituent colors, scientists can reveal a wealth of information about their makeup. This technique allows astronomers to identify the unique fingerprints of various elements and molecules present in these distant objects, based on how they absorb or emit light at specific wavelengths. When light from a star passes through a prism or a diffraction grating, it creates a spectrum, much like a rainbow. Different elements emit or absorb light at particular wavelengths, which appear as distinct lines in the spectrum. By comparing these lines with known wavelengths from laboratory experiments on Earth, astronomers can determine what elements exist in a star or galaxy, including hydrogen, helium, carbon, and many others. This process opened a new window into the cosmos, allowing us to gather vital information without needing to visit these celestial bodies directly. Moreover, spectroscopy has not only helped identify elements, but also revealed other critical details, such as temperature, density, and even motion. For instance, the shifting of spectral lines, known as the Doppler effect, tells us if a star is moving towards us or away from us. This information contributes significantly to understanding the expansion of the universe and the dynamics of galaxies. As we analyze the light from increasingly distant objects, spectroscopy provides crucial evidence regarding the history and evolution of the cosmos. Spectroscopy has transformed the field of astronomy. By unlocking the secrets contained in the light of distant stars and galaxies, it has allowed us to map the universe's composition and gain insights into its fundamental nature. Each spectrum collected is a treasure trove of information, reminding us of how profoundly interconnected we are with the cosmos. When astronomers look out into the vast expanses of the universe, they often come across vast regions known as cosmic voids. These are enormous spaces that contain very few galaxies and significantly less matter compared to the denser regions of the universe where galaxies cluster together. Discovering these cosmic voids helps scientists comprehend the large-scale structure of the universe, much like understanding the layout of a city by examining the areas with and without buildings. Void discovery illuminates the intricate web-like structure of the cosmos. Galaxies do not exist in isolation. Instead, they are part of a great cosmic tapestry, often referred to as the cosmic web. This web comprises filaments of dark matter and galaxies, separated by these expansive voids. By mapping the locations and sizes of these voids, scientists gain crucial insights into the distribution of matter in the universe, which informs our understanding of how the universe evolved over billions of years. Furthermore, voids are fascinating because they challenge and enhance our theories of cosmology. They serve as natural laboratories where the effects of gravity are minimal compared to denser regions. Studying them allows researchers to test models of how matter clumps together and how dark energy influences the universe's expansion. The existence and characteristics of these voids can offer vital clues about the fundamental forces that shape the universe. Cosmic voids are more than just empty spaces. They are key players in understanding the universe's architecture. Their study sheds light on the forces of gravity and dark energy, helping scientists unlock the mysteries of our cosmos and revealing how structure forms over cosmic time. Through this ongoing exploration, we inch closer to understanding the very nature of the universe itself. The quest to detect gravitational waves has seen remarkable advancements over the past few years, ignited by the groundbreaking observations made by the LIGO detectors in 2015. For the first time, scientists confirmed the existence of these ripples in spacetime, created by catastrophic events such as merging black holes or neutron stars. This discovery not only confirmed predictions made by Albert Einstein a century earlier, but opened an entirely new window into the universe, allowing us to hear the cosmic symphony of celestial events. Following LIGO's success, a network of observing facilities, including Virgo in Italy and later CAGRA in Japan, came online. These observatories work in tandem to increase the number of events we can detect. The sensitivity of these instruments has improved dramatically, enabling us to pick up fainter signals than ever before. This enhanced capability means that astronomers can now observe more distant and intriguing events in the universe, examining phenomena that were previously hidden from us. The impact on astronomical studies has been profound. Gravitational wave astronomy is providing insights into the behavior of black holes, the formation of neutron stars, and the mechanics of supernova. When paired with traditional electromagnetic observations, such as light from stars, these waves allow scientists to piece together a more complete story about the life cycles of stars and the dynamics of galaxies. It represents a paradigm shift in how we study the cosmos, focusing on the physical processes that govern the universe's most dramatic events. Moreover, gravitational wave detections spark the imagination and push technological boundaries as researchers develop better and more sensitive detectors. The future of gravitational wave astronomy promises even greater discoveries, possibly leading to new understandings of dark matter, dark energy, and even the origins of our universe itself. Each discovery feeds into a larger tapestry of cosmic knowledge that not only enriches our understanding of the universe, but also continually inspires curiosity about what lies beyond our current grasp. Advancements in computational modeling have revolutionized our understanding of cosmic events by providing powerful tools for simulating complex astronomical phenomena. In the past, scientists relied primarily on observations and simple mathematical equations to inform their predictions about events like supernova explosions, galaxy formation, and black hole dynamics. Today, thanks to improved computer processing power and sophisticated algorithms, researchers can create highly detailed models that incorporate vast amounts of data and represent the intricate workings of the universe. These computational models allow scientists to explore scenarios that would be impossible to test in reality. For instance, simulations can depict the collision of galaxies, helping researchers study how these massive structures evolve over time, merge, and interact with surrounding space. Such models provide insights into not only the physical processes involved, but also the resulting formation of stars and the distribution of dark matter, which by itself remains one of the universe's great mysteries. Moreover, computational modeling has significantly enhanced our ability to predict celestial events, such as gravitational waves produced by colliding black holes or neutron stars. By understanding the dynamics of these systems through simulation, scientists can better prepare for and interpret real observations made by instruments like LIGO and Virgo. The insights gained from these simulations also help refine our theoretical frameworks, pushing the boundaries of what we know about the fundamental forces that govern the cosmos. As we continue to improve our computational capabilities, the intertwining of computer science and astrophysics promises to unlock new discoveries. With each leap in technology, we inch closer to answering profound questions about the origins of the universe and the nature of phenomena yet to be fully understood. The cosmos may be vast and enigmatic, but through the power of computational modeling, we can explore its depths with unprecedented clarity and precision. Telescopes have revolutionized our understanding of the universe, and their ability to operate across different wavelengths of light allows us to see beyond what the human eye can perceive. Each part of the electromagnetic spectrum, ranging from radio waves to gamma rays, provides unique insights into celestial objects. While visible light can tell us about a star's color and temperature, other wavelengths reveal different facets of the same objects, painting a more complete picture of the cosmos. For instance, radio telescopes can detect cosmic phenomena that are invisible to optical telescopes. They have uncovered vast clouds of gas and dust where new stars are birthing. This ability to peer into dark regions of space allows astronomers to study the early stages of stellar evolution. Similarly, infrared telescopes can penetrate the dense clouds of gas and dust surrounding newly forming stars, revealing the hidden architectures of galaxies and the processes that fuel star formation. On the other end of the spectrum, gamma-ray telescopes provide insights into some of the universe's most violent events, such as supernova explosions or the vicinity of black holes. These high-energy emissions illuminate the processes that occur under extreme conditions, helping scientists understand the fundamental physics at play. By analyzing data from these various sources, astronomers can piece together a comprehensive view of celestial phenomena, enriching our knowledge of the universe's complexities. Utilizing telescopes that observe across the electromagnetic spectrum allows scientists to create a multidimensional view of the cosmos. Each wavelength acts like a different tool in an astronomer's toolkit, enabling them to gather information that would otherwise remain hidden. This interdisciplinary approach underscores the intricate beauty of the universe and emphasizes how interconnected all forms of observation are in the quest for cosmic knowledge. In recent years, advancements in satellite technology have revolutionized how researchers observe and analyze the wonders of our universe. One of the key innovations is the development of more sensitive detectors and cameras. These devices can capture faint light from distant celestial objects, allowing astronomers to study phenomena that were once too dim to observe. With these sophisticated instruments, scientists can gather data across various wavelengths, including visible light, ultraviolet, and infrared, unveiling different aspects of cosmic phenomena. Another significant leap has come from the introduction of adaptive optics in satellite technology. Originally developed for ground-based telescopes, adaptive optics can now be integrated into satellite systems. This technology compensates for the blurring effects of Earth's atmosphere, producing sharper images. The increased clarity means that researchers can observe details of galaxies, nebulae, and other astronomical features, leading to new discoveries about their structure and behavior. Furthermore, the advent of small satellites, or CubeSats, has opened up new opportunities for space exploration. These compact, cost-effective satellites can be deployed en masse to monitor specific regions of space or carry out targeted experiments. Their flexibility allows scientists to gather real-time data about cosmic events like supernovae or the movement of asteroids. It's like having a swarm of mini-observers continuously gathering information from different perspectives. Finally, the connectivity of satellites with ground stations has improved dramatically, enabling faster data transmission. This rapid exchange of information allows researchers to respond swiftly to cosmic events, enhancing our understanding of phenomena such as gamma-ray bursts and gravitational waves. With these innovations, we are not just looking at the universe, we are peeling back its layers to reveal the secrets of its formation and evolution. Each breakthrough brings us closer to comprehending the vast cosmos that surrounds us. Interferometers are remarkable instruments that enhance our ability to detect faint signals from the depths of space. They operate by combining the light or radio waves received from celestial objects by multiple telescopes spread over a substantial distance. This setup allows scientists to notice minute variations in the signals, effectively amplifying the information we can gather from distant stars, galaxies, and other cosmic phenomena. One of the key advantages of this array system is its ability to improve resolution, which is particularly crucial when studying faraway objects. Just as two ears can help locate the direction of a sound more accurately than one, multiple telescopes working together can pinpoint the origin of light with much greater precision. This technique means that astronomers can differentiate between closely spaced objects that would otherwise appear as a single entity in a traditional telescope. Additionally, interferometers can filter out noise from the environment and the atmosphere, which can often obscure signals coming from space. By synchronizing the observations from each telescope and combining them into a single image or dataset, researchers can isolate the subtle signals they are looking for. This capability opens up the universe, revealing details about cosmic events such as the flicker of distant stars or the faint whispers of gravitational waves. Ultimately, interferometers have transformed our understanding of the universe. They have allowed us to observe and study features that were once beyond our reach, leading to groundbreaking discoveries across fields such as astrophysics and cosmology. With these advanced tools, we are continually pushing the boundaries of our knowledge about the universe and our place within it. Astronomers face a fascinating array of challenges when studying cosmic events that unfold across immense distances. One of the primary hurdles is the sheer scale involved. The universe is so vast that even light, which travels at an extraordinary speed, can take millions or billions of years to reach us from the farthest cosmic objects. This means that when we observe distant galaxies or supernovae, we are actually seeing them as they were in the distant past, not as they are today. This time delay complicates our understanding of cosmic evolution and the life cycles of celestial bodies. Another significant challenge concerns the faintness of distant cosmic events. As light travels through space, it loses intensity and can be affected by various factors, such as cosmic dust or intervening objects. This dimming makes it difficult for astronomers to detect or observe events that are far away. Special instruments such as powerful telescopes and sophisticated detectors are required to capture these faint signals. This need drives the continuous development of technology and observation techniques in the field of astronomy, pushing the boundaries of our capabilities. Additionally, the vast distances pose a challenge in terms of communication and collaboration. When cosmic events occur, data must be gathered, analyzed, and shared among scientists around the globe. Coordinating such efforts can be complex, particularly when immediate reactions or observations are required. Astronomers often rely on networks and collaborations that span continents, sharing information and resources to enhance our understanding of these cosmic phenomena. Despite these challenges, the universe offers a treasure trove of mysteries waiting to be unlocked. Each observation made by astronomers brings us a step closer to understanding the fundamental processes that govern the cosmos. As technology advances and our collaboration improves, we inch toward unveiling the secrets of the universe, revealing not only its vastness but also our place within it. The development of adaptive optics has revolutionized ground-based astronomy in remarkable ways. Historically, astronomers faced significant challenges due to the blurring effects of Earth's atmosphere. Light from distant stars and galaxies would distort as it passed through the turbulent layers of air, which rendered images fuzzy and difficult to interpret. Traditional telescopes were unable to overcome this issue, which limited the clarity of observations from Earth. Adaptive optics technology addresses this problem by using a system of mirrors that can change shape in real time. These mirrors compensate for atmospheric distortions by actively adjusting to the ever-changing conditions of the air above. By observing a nearby reference star, the system can measure the distortions caused by the atmosphere and then correct the incoming light in an instant. As a result, astronomers can achieve images that are comparable to those obtained from space telescopes. This innovation has enabled scientists to peer deeper into the cosmos, revealing intricate details of celestial objects that were previously obscured. For instance, the sharp images produced by adaptive optics have allowed researchers to study the structure of distant galaxies, the formation of stars, and even the atmospheres of exoplanets. This profound clarity has expanded not only our understanding of the universe, but also sparked new questions about its formation and evolution. Furthermore, adaptive optics systems are continuously advancing, becoming more sophisticated and more widely used in observatories around the globe. With each enhancement, they enable more detailed investigations and exciting discoveries, continuously enriching our exploration of the night sky and transforming our view of the universe's vast mysteries. This technology has truly opened up a new realm for ground-based astronomy, bridging the gap between terrestrial and astronomical observations. Across the globe, scientists have recognized that collaboration is key to tackling the complexities of astrophysics. Institutions, researchers, and observatories have come together to share their knowledge, resources, and discoveries. One notable example is the United Nations International Scientific Council, which connects space agencies and research institutions worldwide. This cooperative framework allows for collective missions and shared funding, amplifying the work being done in the field. One significant example of global collaboration is the Event Horizon Telescope project. This ambitious initiative united many institutions across continents to capture the first image of a black hole. By synchronizing radio telescopes from Hawaii to Europe, researchers created a virtual Earth-sized telescope. This collaborative effort not only pushed the boundaries of technology, but also forged new relationships among scientists dedicated to unraveling the mysteries of black holes. Another remarkable partnership can be found in the European Southern Observatory, which brings together 20 countries to operate some of the most advanced telescopes in the Southern Hemisphere. With shared expertise and resources, member nations have made groundbreaking discoveries, including exoplanets and insights into dark energy. These advancements have significant implications for our understanding of the universe and our place within it. Furthermore, multinational initiatives like the Laser Interferometer Gravitational Wave Observatory have revolutionized how we detect astronomical phenomena. By collaborating across borders to refine gravitational wave detection, scientists have opened a new window onto the universe, allowing us to observe events like black hole mergers and neutron-star collisions. This collaborative spirit continues to bear fruit, highlighting how unity in the scientific community can lead to significant advancements that propel astrophysics into new realms of understanding. In recent decades, the collaboration among international space agencies has revolutionized our efforts to explore and study distant planets. This teamwork is not just a matter of pooling resources. It allows scientists and engineers from diverse backgrounds to share expertise, technology, and innovative ideas. Each agency contributes unique strengths, be it NASA's experience, the European Space Agency's strategic vision, or the advancements from space agencies in countries like India and China. One remarkable illustration of this collaboration is the Mars exploration missions. Different countries have brought their spacecraft to Mars, each designed for specific objectives. For example, while NASA's Perseverance rover focuses on searching for signs of ancient life, the United Arab Emirates Hope orbiter gathers valuable atmospheric data. These data points work in concert, providing a more comprehensive understanding of the Martian environment and its potential for hosting life. Additionally, shared missions are becoming more common. The James Webb Space Telescope, developed through a partnership between NASA, the European Space Agency, and the Canadian Space Agency, exemplifies this approach. By uniting resources and knowledge, the agencies enhance the spacecraft's capabilities. This telescope promises to revolutionize our understanding of not just distant planets, but the very formation of the universe itself. The benefits of this collaborative spirit extend beyond the immediate scientific goals. They foster a sense of global unity, demonstrating that when we work together, we can address complex challenges that no single nation can tackle alone. By combining insights and techniques from around the globe, we enhance our ability to explore the cosmos, revealing the secrets of distant planets and perhaps uncovering new worlds teeming with the possibility of life. Sharing data and resources among diverse scientific fields has become an essential strategy in unraveling the mysteries of the cosmos. When scientists from various disciplines collaborate, they bring unique perspectives and tools to the table, enhancing the overall understanding of complex astronomical phenomena. For example, the fusion of astrophysics with computer science has led to more advanced simulations, allowing researchers to model cosmic events that would otherwise remain a mystery. This interdisciplinary approach enables the identification of patterns and connections that might not be visible within a single field alone. Consider how data from particle physics can illuminate our understanding of dark matter. Scientists examining high-energy particle collisions can yield insights that help astrophysicists study the vast cosmos where dark matter interacts. These collaborative efforts are critical for piecing together the intricate puzzle of the universe. Moreover, shared resources provide access to cutting-edge technology and databases that improve research quality. Large telescopes, observational data, and even space missions can be utilized across scientific communities, creating a wealth of information that fuels discoveries. For instance, the gravitational wave observatories and their datasets have proven invaluable, not only for astrophysics, but also for fields like general relativity and cosmology, all sharing the common goal of understanding the fabric of space and time. The collaboration across varied scientific fields creates a vibrant ecosystem of knowledge. By uniting their efforts, scientists can tackle cosmic mysteries in innovative ways, pushing the boundaries of human understanding. Such synergy reveals that when science transcends individual disciplines, it fosters groundbreaking discoveries that benefit not only the scientific community, but also enrich our collective understanding of the universe. Educational outreach programs play a crucial role in igniting curiosity about astronomy and space science. By engaging people in their natural environments, such programs bring the wonders of the universe closer to individuals who might not otherwise have access to these fascinating topics. Whether through school visits, community workshops, or interactive exhibits at science centers, these initiatives make the cosmos accessible and relatable. One of the most effective methods these programs use is hands-on experiences. When participants can touch a meteorite or peer through a telescope, they establish a personal connection to the universe. This experiential learning fosters a deeper understanding and creates memorable moments that inspire further exploration. Moreover, these programs often cater to various age groups, from children to adults, ensuring that everyone can appreciate the beauty and complexity of space. Additionally, outreach programs often collaborate with local educators to develop tailored curricula that align with academic standards. This approach not only enhances the classroom experience, but also bridges the gap between formal education and enthusiastic exploration. By introducing astronomy in a way that complements what students learn in school, these initiatives cultivate a lasting interest that can lead to future careers in science, technology, engineering, and mathematics. Finally, the wonder of the night sky itself serves as a powerful motivator. Events like star parties or public lectures amplify community engagement, allowing participants to share their awe and excitement with others. As people come together to explore the cosmos, they build a shared appreciation for our place in the universe, fostering a sense of community and shared responsibility for the future of space exploration. Ultimately, educational outreach programs not only spark interest, but also empower individuals to become lifelong learners and advocates for science. Citizen science projects have become a fundamental pillar in expanding our data collection efforts in cosmic exploration. These initiatives invite members of the public to participate actively in scientific research, allowing for a wealth of data to be gathered that would otherwise require significant resources and time to collect. By leveraging the enthusiasm and diverse skill sets of everyday individuals, scientists can engage a broader community in the exploration of the universe. One striking example comes from projects like Galaxy Zoo, where volunteers help classify galaxies based on images captured by telescopes. This project alone has helped categorize millions of galaxies, accelerating the pace of discovery in our understanding of the cosmos. Each classification made by a citizen scientist contributes to creating a more detailed picture of how galaxies form and evolve, enriching our knowledge at a fraction of the cost and time needed for traditional scientific methods. Moreover, citizen science projects harness the power of technology, as individuals often use their personal devices for data analysis. With access to online platforms and applications, they can engage with real data from telescopes and spacecraft. This interaction not only expands the dataset available to researchers, but also fosters a sense of community and collaboration among enthusiasts from various backgrounds, reinforcing the notion that everyone can contribute to the advancement of science. Importantly, citizen science enhances public engagement with science and astronomy. As people contribute to data collection and analysis, they develop a deeper appreciation for the universe and the scientific process. This democratization of science transforms passive spectators into active participants, encouraging lifelong curiosity and potentially inspiring future generations of scientists eager to explore the mysteries of the cosmos. The role of citizen science, therefore, is not just about collecting data, It's about building a collective effort to understand our universe more profoundly. The next generation of missions targeting Mars is set to push the boundaries of our understanding of the Red Planet like never before. As we stand on the threshold of these ambitious explorations, the objectives range from searching for signs of past life to preparing for future human exploration. These missions are designed to build on the successes of previous rovers and orbiters, paving the way for exciting discoveries. One of the key goals is to return samples from Mars to Earth. Various missions are on the horizon, particularly through partnerships like NASA's Mars Sample Return Program and the European Space Agency's contributions. These missions will not only gather rock and soil samples, but also transport them back to our laboratories for comprehensive analysis. This could provide definitive proof of whether life ever existed on Mars and offer insights into the planet's geological history and climate evolution. Additionally, there is a strong focus on studying Mars' atmosphere and climate. Upgraded instruments and new satellite missions aim to analyze weather patterns and trace gases such as methane, which intriguingly varies in concentration and could hint at biological processes. Understanding these atmospheric dynamics is crucial as they may affect future human missions, especially in finding resources like water or identifying suitable landing sites. Finally, the next generation of Mars missions will emphasize technology development that will support human exploration. Missions like those involving advanced habitats and life support systems are in the works, setting the stage for a crewed presence on Mars by the next decade. The knowledge gained from these endeavors will not only advance our understanding of our neighboring planet, but also enrich our quest to explore deeper into the solar system. Each mission brings us closer to unlocking the mysteries of Mars and potentially our own origins. Scientists assess the potential for life on other planets by examining a range of key factors that contribute to habitability. These include the presence of liquid water, suitable temperatures, and the right atmospheric conditions. By focusing on these essential ingredients, researchers can narrow down candidates where life might exist, either currently or in the past. In our own solar system, locations like Mars and the icy moons of Jupiter and Saturn, such as Europa and Enceladus, have garnered significant interest. Mars, with its ancient riverbeds and signs of past water flow, presents intriguing possibilities. Europa, covered in a thick layer of ice, is thought to have an ocean beneath that surface, potentially rich in nutrients. These environments make scientists eager to explore further, often turning to robotic missions to gather more data. Beyond our solar system, the search for exoplanets, those orbiting other stars, has become a vital part of the quest for extraterrestrial life. Astronomers employ advanced telescopes to identify planets in the so-called Goldilocks zone, where conditions may be just right for life as we know it. By studying the atmospheres of these distant worlds, looking for chemical signatures indicative of biological processes, scientists can make educated guesses about the likelihood of life existing there. The quest is ongoing, with scientists utilizing data from space missions, advanced telescopes, and laboratory experiments on Earth to build a comprehensive picture. Each discovery not only broadens our understanding of where life could exist, but also deepens the mystery of our universe, reminding us that we are merely on the periphery of understanding the cosmos and our place within it. Future missions to study asteroids present an incredible opportunity to deepen our understanding of the solar system and our own planet's history. These ancient celestial bodies are remnants from the early formation of the solar system, containing clues about its origins and evolution. By analyzing the materials found in asteroids, scientists can uncover information about the building blocks of planets, including Earth, and unravel mysteries related to the formation of life itself. One significant breakthrough could be the development of advanced mining techniques. As Earth's resources become increasingly limited, asteroids may serve as a treasure trove of valuable materials, such as rare metals and water. Water, in particular, is a game changer for space exploration, as it can be converted into hydrogen and oxygen to produce rocket fuel, potentially enabling longer missions to Mars and beyond. It offers the prospect of supporting human life in space, making astromining an exciting frontier for future innovations. In addition to resource extraction, studying asteroids can enhance our ability to predict and prevent potential Earth impacts. Understanding the composition and trajectory of particularly dangerous asteroids allows scientists to devise strategic plans to deflect or alter their paths, safeguarding our planet from catastrophic collisions. Missions like these are not purely about potential threats. They can foster collaboration among nations and spur technological advancements applicable to various fields on Earth. Lastly, exploring the chemistry and geology of asteroids can offer insights into the potential for life beyond our planet. Some asteroids may harbor organic compounds, and understanding these materials could inform our theories about how life began on Earth and whether it exists elsewhere in the universe. Future missions to asteroids promise not only to enhance our scientific knowledge, but also to shape the trajectory of our civilization in space exploration and resource management. The study of lunar geology offers a unique window into the history of our solar system. The Moon, with its ancient surface, is a record keeper of geological events that have taken place over billions of years. Unlike Earth, which is constantly reshaped by weather, erosion, and tectonic movements, the Moon's surface is relatively stable. This allows scientists to study its craters, volcanic features, and rock formations without the interference of newer geological processes. By examining the Moon's surface, researchers can learn about the timing and impact of significant events, such as asteroid impacts that shaped not just the Moon, but also the Earth and other celestial bodies. The craters that dot the lunar landscape provide clues about the frequency and scale of these collisions. Each crater tells a story, from the size of the impactor to the age of the surface layer, helping scientists to piece together the chaotic early history of the solar system. Moreover, lunar samples brought back by missions like Apollo have revealed a wealth of information about the Moon's composition. These samples allow scientists to date various formations and infer the processes that formed them, shedding light on the conditions of the early solar system. For instance, finding ancient volcanic rocks can help us understand the thermal history of the Moon, which in turn allows us to draw parallels with the geological evolution of other planets and moons. Additionally, insights from lunar geology can inform us about the potential for resources in space. As we consider future explorations and even colonization, understanding the Moon's materials, such as water ice in shadowed craters, becomes critical. The Moon serves as both a historical record and a stepping stone for humanity's next adventures in space, making lunar geology an essential field in unraveling the broader narrative of our cosmic neighborhood. As humanity looks towards the stars, a wave of innovative technologies is emerging to bolster our ability to explore space. One of the most exciting developments is in propulsion systems. Traditional rocket engines, while effective, are limited by their fuel capacity and speed. Advances in electric propulsion are offering pathways to faster and more efficient travel. These systems can utilize sunlight or other energy sources to accelerate spacecraft, reducing travel time to distant destinations such as Mars. Life support technology is also undergoing significant improvements. Creating sustainable habitats for astronauts is crucial for long missions, particularly on planets like Mars. New environmental control systems are in development, designed to recycle air and water more efficiently, ensuring that humans can thrive in the harsh conditions of space. These systems aim to create a closed-loop environment, minimizing reliance on resupply from Earth, which is vital for long-duration missions. Robotics and automation are set to play a pivotal role in space exploration as well. Autonomous robots can perform tasks that are too dangerous or tedious for humans, ranging from surface exploration to constructing habitats. Advanced robotics will also facilitate the gathering of scientific data and samples, enabling missions to be more efficient and productive. With capabilities to operate in remote or hazardous environments, these machines will be essential companions to human astronauts. Finally, there's a focus on biotechnology and materials science. Researchers are exploring how to use materials available on other planets to build structures or create necessary tools. This approach, known as in situ resource utilization, could significantly reduce the amount of equipment that must be transported from Earth. At the same time, new biotechnological advancements could help us grow food in space, making long-term habitation a feasible reality. Collectively, these advancements form a foundation on which the next era of human space exploration can be built, making our dreams of exploring the cosmos more tangible than ever before. Throughout history, various artifacts from ancient civilizations have provided profound insights into how early humans perceived the cosmos. One of the most iconic examples comes from ancient Mesopotamia, where cuneiform tablets reveal detailed records of celestial observations. The Babylonians, in particular, had a keen interest in the movements of celestial bodies, developing complex systems to track the stars and planets. They noted patterns and cycles, showcasing a sophisticated understanding of astronomy that influenced their agricultural practices and religious rituals. In ancient Egypt, the construction of the pyramids is a fascinating testament to cosmic intrigue. These grand structures were aligned with precise astronomical phenomena, such as the rising and setting of stars. The Great Pyramid of Giza, for instance, is aligned with incredible accuracy to the cardinal points. This alignment was not merely a matter of aesthetics. It reflected a belief in the celestial order and its relationship to the afterlife, as inhabitants looked to the stars for guidance and meaning. The Mayans and the Aztecs of Mesoamerica also left behind artifacts revealing their cosmic observations. The Mayan calendar is a remarkable example, intricately crafted and reflecting their deep understanding of time based on celestial cycles. This system incorporated the movements of the sun, moon, and planets into its structure, directly linking their cosmology to daily life and agriculture. The orbital or stone of the sun, used by the Aztecs, serves a similar purpose, illustrating their reverence for celestial events like solstices and equinoxes. Each of these ancient artifacts tells a story about humanity's quest to understand our place in the vast universe. From aligning monumental architecture with the cosmos to developing complex calendars that track time, these civilizations showcased a profound connection to the skies above. Their insights remind us that even in ancient times, the stars were a source of awe and wonder, shaping cultures and guiding lives in ways we are still uncovering today. The methods we use to date cosmic events have evolved remarkably over time, reflecting our growing understanding of the universe. In the early days of astronomy, celestial events were often dated based on their proximity to earthly occurrences. Ancient civilizations relied on observations of the stars and planets, using calendars based on the cycles of the moon and sun. This primitive method provided a way to mark time, but lacked the precision needed for deeper cosmic studies. As technology advanced, so did our techniques. The advent of telescopes in the 17th century allowed astronomers to observe celestial bodies in greater detail, leading to more established methods of dating. By studying the light emitted by stars and galaxies, scientists could begin to gauge their distance from Earth. The concept of light years emerged, with astronomers realizing that the light from distant stars takes millions or even billions of years to reach us, inherently providing a cosmic timestamp for their existence. The discovery of radioactivity in the 19th century further revolutionized our dating methods. The ability to measure the decay of radioactive isotopes allowed scientists to date materials like rocks and meteorites using the principle of half-lives. This changed the game for understanding the age of our planet and the solar system. Combining these geological dating methods with astronomical observations, researchers have since determined ages for galaxies, stars, and even cosmic events like supernova. Today, we incorporate advanced technologies like computer simulations and data from space telescopes, allowing for unparalleled precision. The evolution of these dating methods tells us not only about the timeline of the universe, but also about our persistent curiosity and ingenuity. Each new method unveils more about the cosmos, reminding us of the vastness of time and the complexity of the universe we inhabit. This ongoing journey of discovery continues to deepen our appreciation of our place within the cosmic tapestry. Fossil records provide an extraordinary glimpse into the history of life on our planet, revealing the existence of primordial life forms that thrived billions of years ago. These ancient fossils, which include simple organisms such as bacteria and algae, tell a story that stretches back over 3.5 billion years. These early life forms played a crucial role in shaping Earth's environment, laying the foundation for the diverse ecosystems we recognize today. The implications of discovering these primordial life forms are profound. First, they challenge our understanding of life's resilience and adaptability. These organisms survived and thrived in harsh conditions, including extreme temperatures and lack of oxygen. This suggests that life is remarkably tenacious and may arise in even the most inhospitable environments, prompting scientists to reconsider where and how life might exist beyond our planet, such as on Mars or the moons of Jupiter and Saturn. Moreover, these fossil findings push us to re-examine evolutionary timelines. The earliest organisms were likely prokaryotic, meaning they did not have a nucleus in their cells, which is a defining characteristic of more complex life forms that appeared later. By understanding the characteristics and activities of these primordial life forms, researchers can gain insights into the evolutionary processes that led to the emergence of more complex organisms, including plants, animals, and eventually humans. Lastly, these fossil records serve as a vital resource for understanding the history of Earth's climate and its long-term changes. The metabolic activities of ancient life forms were instrumental in altering the planet's atmosphere and contributing to the formation of essential elements, such as oxygen. This interplay between life and the environment continues to resonate in ongoing discussions about climate change and biodiversity, reminding us of the critical relationship that exists between living organisms and their surroundings. The story of primordial life, thus, not only enriches our scientific knowledge, but also deepens our appreciation for the intricate web of life that has evolved on Earth. Stellar archaeology is an intriguing field that allows scientists to piece together the history of the universe by studying the remnants of ancient stars. Just as traditional archaeology digs into the past through artifacts to uncover human history, stellar archaeology examines the chemical signatures and motions of stars to unlock clues about the cosmos's evolution. Each star carries with it a record of the processes that shaped it, revealing vital information about the characteristics of the galaxy and the universe at various epochs. One particularly fascinating aspect of stellar archaeology is the study of metal content in stars. Many of the oldest stars, known as population 2 stars, formed when the universe was relatively young and had low metal levels, reflecting an early state of cosmic chemistry. By mapping these stars and analyzing their elemental makeup, astronomers can infer the conditions prevalent at the time of their formation. For instance, a star with very little iron suggests that it was born in an era when few supernovae had occurred, as these explosive events are crucial for dispersing heavier elements into the galaxy. In addition to chemical analysis, the movement of stars across the galaxy helps researchers trace the history of cosmic events. Stars that travel in similar paths may have originated from the same region of space or experienced related events, such as galactic mergers. By understanding the dynamics of these stellar populations, scientists can reconstruct the history of the Milky Way and its formation, revealing how our galaxy has changed and evolved over billions of years. As technology advances, the tools available for stellar archaeology grow ever more sophisticated. Instruments like powerful telescopes and spectrometers allow for deeper understanding and more precise measurements. In the grand tapestry of the universe, each star tells its own story, and by gathering these narratives, we gain a richer appreciation of our cosmic origins and the intricate processes that have unfolded across time and space. The cosmic microwave background radiation, or CMB for short, is a remarkable relic from the universe's infancy. It is a faint glow left over from the hot, dense state of the early universe, which existed just a few 100,000 years after the Big Bang. This ancient radiation fills the universe and provides scientists with a snapshot of the cosmos during its formative years. By studying the features of this radiation, researchers have gleaned vital information about the conditions that prevailed when the universe first began to cool and expand. One of the most significant revelations from the CMB is the uniformity of the universe. When we examine the temperature fluctuations in the CMB, we see tiny variations, often no more than 1 part in 100,000. These small irregularities are believed to reflect the initial density fluctuations that eventually gave rise to the vast structure of galaxies and clusters we observe today. The CMB acts like a cosmic map, showing how matter was distributed in the early universe and setting the stage for the formation of stars and galaxies. Moreover, the CMB tells us about the universe's age and its overall composition. Current measurements indicate that the universe is about 13.8 billion years old. This information has been critical in piecing together the timeline of cosmic events, from the Big Bang to the formation of the first galaxies. Furthermore, the CMB provides evidence for the presence of dark matter and dark energy, components that together make up about 95% of the total energy content of the universe, profoundly impacting its expansion and fate. Finally, the discovery and analysis of the cosmic microwave background radiation have revolutionized cosmology, allowing scientists to test various theories about how our universe operates. By combining the data from the CMB with other astronomical observations, researchers are unraveling the mysteries of the cosmos, piecing together not just where we come from, but where we might be headed in the vast expanse of space and time. In this sense, the CMB is not merely a remnant, it is a key that unlocks the secrets of the universe's origins and its ongoing evolution. The idea of dark matter arose from puzzling observations in the universe that challenged our understanding of gravity and visible matter. One compelling piece of evidence comes from the rotation curves of galaxies. When astronomers measure the speed at which galaxies spin, they notice that stars on the outer edges rotate much faster than we would expect based on the visible mass alone. This discrepancy suggests that there is an unseen mass, dark matter, providing the additional gravitational pull needed to hold these galaxies together. Another significant line of evidence for dark matter is found in the study of galaxy clusters. These massive groups of galaxies exhibit gravitational effects that cannot be accounted for by the visible matter within them. Observations of how light from distant galaxies bends, an effect known as gravitational lensing, indicate that there is more mass present than what we can see. The lensing effect occurs because light travels along curved paths in a gravitational field, making the presence of dark matter crucial for explaining these observations. Dark matter also plays a vital role in the formation of large-scale cosmic structures. Simulations of the universe's evolution show that this mysterious substance is essential for the clumping of matter, leading to the formation of galaxies and galaxy clusters over billions of years. Without dark matter, the universe as we know it would not exist. Galaxies would be too dispersed, unable to form into the rich tapestry of structures we observe today. The evidence supporting dark matter is found through its gravitational effects across different scales, from the rotation of galaxies to the behavior of massive clusters. Understanding dark matter is not merely an academic endeavor, it is crucial for unraveling the mystery of how cosmic structures came to be and the overall dynamics of the universe. The quest to understand dark matter continues to inspire astrophysicists and cosmologists alike, as it holds the keys to some of the most significant questions about the nature of reality. The cosmos we inhabit is a magnificent tapestry woven from various elements, among which dark energy and matter play pivotal roles in shaping its destiny. Matter, which includes stars, planets, and galaxies, has a gravitational influence that pulls objects together. In contrast, dark energy, a mysterious force constituting about 70% of the universe, has the opposite effect. It is believed to drive the acceleration of the universe's expansion, a discovery that shocked scientists in the late 20th century when they observed galaxies receding from one another faster than previously anticipated. As the universe expands, dark energy exerts a powerful influence over its dynamics. While matter clusters together due to its gravitational pull, dark energy works silently yet effectively to push those clusters apart. This interaction creates a balance where initially the gravitational forces of matter had a dominant role. Over time, as the universe grew and matter became more spread out, dark energy began to dominate, causing an acceleration in the rate of expansion. An intriguing aspect of this interaction is how it affects the formation and evolution of structures within the universe. In the early cosmos, matter was dense, enabling the formation of galaxies and large-scale structures through gravitational attraction. However, as dark energy began to assert itself more strongly, it prevented structures from growing indefinitely. This means that while galaxies continue to form and evolve, they must contend with the ever-present stretch of space itself, which affects their interaction and connectivity. Ultimately, the interplay between dark energy and matter provides us with profound insights into the fate of the universe. If dark energy continues to push against matter, we may witness a future where galaxies are isolated islands drifting further apart in an ever-expanding cosmos. Understanding this delicate balance is not merely an academic pursuit. It opens a window into the very nature of our universe and continues to beckon scientists to unravel its lingering mysteries. The quest to uncover the mysterious nature of dark matter is one of the biggest challenges in modern physics, and scientists around the world are implementing a variety of innovative experiments to directly detect dark matter particles. One of the most notable experiments is located deep underground at the SNOLAB facility in Canada. Known as the SNO+ experiment, it employs large volumes of liquid scintillator aimed at identifying rare interactions between dark matter particles and regular matter. By isolating these interactions from cosmic rays and other background noise, researchers hope to catch a glimpse of elusive dark matter. Another significant initiative is the Lux-Zeppelin experiment based in South Dakota within the Homestake mine. The Lux-Zeppelin experiment uses advanced detection technologies to search for weakly interacting massive particles, or WIMPs, which are among the leading candidates for dark matter. This experiment utilizes a massive tank filled with liquid xenon, allowing scientists to monitor potential interactions. If a dark matter particle were to collide with a xenon nucleus, it would create a detectable signal. This project is a collaboration among scientists from across the globe and aims to enhance our understanding of dark matter. Across the ocean in Italy, the Dark Side collaboration is making strides at the Gran Sasso National Laboratory. Much like its counterparts, Dark Side seeks to identify WIMPs by utilizing a dual-phase argon detector. What sets Dark Side apart is its unique method of purifying argon to reduce background interference, maximizing its chances of detecting dark matter signals. This meticulous approach reflects the ongoing efforts to create the most controlled environment possible for these measurements. Additionally, the CASPER experiment, short for Cosmic Axion Spin Precession Experiment, seeks to explore axions, another potential dark matter particle. This experiment strives to determine if axions can heat up conditions that are detectable. The diversity of strategies across these experiments, from using lux and argon to delving into spin precession, showcases the rich tapestry of research focused on revealing the fundamental essence of dark matter. The results of these studies could reshape our understanding of the universe and the very fabric of reality. Dark energy remains one of the universe's most profound mysteries, and studying its effects on celestial bodies involves a combination of observational techniques and theoretical models. Scientists primarily utilize telescopes to gather data from distant galaxies and cosmic phenomena. By measuring the light from these objects, they can determine their distance from Earth, which is crucial for understanding how dark energy influences the universe's expansion over time. One of the key methods in this endeavor is observing the phenomenon known as redshift. As the universe expands, light from distant galaxies is stretched, causing it to shift toward the red end of the spectrum. By analyzing this redshift, astronomers can infer how fast these galaxies are moving away from us and thus gain insights into the rate of expansion driven by dark energy. This interplay between distance, speed, and light provides a window into the dynamics of dark energy. Another important approach is through studying supernovae, particularly type Ia supernovae. These stellar explosions serve as standard candles for measuring astronomical distances. By examining their brightness and frequency, scientists can track the acceleration of the universe's expansion. This data has suggested that dark energy constitutes about 70% of the universe, profoundly affecting its structure and evolution. Theoretical models also play a significant role. Scientists develop simulations to explore how dark energy might behave under different conditions. By combining these models with observational data, researchers can test hypotheses about dark energy's properties and how it impacts the movement of galaxies and the formation of large-scale structures. This blend of observation and theory is essential in peeling back the layers of one of science's most intriguing enigmas. As we gaze into the cosmos, two of the most baffling mysteries of modern physics stand out: dark matter and dark energy. These elusive entities make up about 95% of the universe, yet their nature remains a profound enigma. To unveil their secrets, scientists around the world are planning and conducting a variety of cutting-edge experiments. One of the most anticipated experiments is the Large Hadron Collider's ongoing attempts to discover new particles that could account for dark matter. With its ability to recreate conditions similar to the moments just after the Big Bang, the collider may uncover weakly interacting massive particles. These particles could be the key to understanding dark matter, which does not emit, absorb, or reflect light, eluding direct detection through conventional means. Additionally, scientists are probing into supersymmetry, a theoretical framework suggesting that every known particle has a heavier yet-to-be-discovered counterpart. If these supersymmetric particles exist, they could provide clues about dark matter's true nature. Deep underground facilities like the Large Underground Xenon experiment are also playing a vital role in our search. By utilizing ultra-sensitive detectors shielded from cosmic rays, scientists aim to identify rare interactions between dark matter particles and normal matter. These detectors are armed with liters of liquid xenon, making them some of the most precise instruments for direct detection efforts. As we better understand the tiny signals that may indicate the presence of dark matter, we inch closer to unraveling its mystery. On the other hand, dark energy, the force believed to drive the accelerated expansion of the universe, poses equally exciting questions. Experiments like the European Space Agency's Euclid satellite and NASA's Wide Field Infrared Survey telescope are set to map the universe's expansion history through detailed observations of galaxy distributions. By analyzing the light emitted from distant galaxies, these missions will help scientists explore the effects of dark energy over cosmic time. As these exciting experiments unfold, we stand on the brink of potentially profound discoveries that could forever reshape our understanding of the universe. The study of extremophiles, organisms that thrive in conditions previously thought to be uninhabitable, has unveiled incredible insights that significantly inform our quest for extraterrestrial life. These remarkable creatures can be found in some of Earth's most extreme environments, such as deep-sea hydrothermal vents, acidic hot springs, and even within the icy realms of Antarctica. Their remarkable adaptability challenges the traditional understanding of the limits of life, suggesting that life could potentially exist in similarly harsh conditions on other planets or moons in our solar system. One of the most striking examples of extremophiles is the tardigrade, often referred to as the water bear. Tardigrades can survive extreme temperatures, radiation, and even the vacuum of space. They enter a state known as cryptobiosis, essentially shutting down their metabolism and preserving their cells. This extraordinary resilience raises the possibility that life forms on other celestial bodies may adapt in unexpected ways to survive their environments, broadening our search parameters beyond the ideal conditions we once considered necessary for life. Moreover, studies of extremophiles have provided valuable insights into biochemistry that could inform the search for extraterrestrial organisms. For instance, some extremophiles harness unique biochemical processes to extract energy from sulfur or iron rather than sunlight. This knowledge encourages scientists to expand their exploration for life beyond the traditional focus on oxygen and water. It prompts us to think about alternative biochemistries that might be present in the subsurface oceans of places like Europa, one of Jupiter's moons, or Enceladus, a moon of Saturn, where conditions may resemble those of the extreme environments we find on Earth. Extremophiles are not just fascinating examples of life's tenacity. They are a beacon guiding our exploration for life beyond our planet. As we continue to study these resilient organisms, we are not only uncovering the possibilities for life in extreme environments here on Earth, but we are also expanding our understanding of where and how we might search for life elsewhere in the universe. This field of research opens up thrilling avenues for discovery, reminding us that life may be more versatile than we ever imagined. In the fascinating field of astrobiology, scientists are constantly seeking answers to profound questions about life beyond Earth. To sift through the vast amounts of data collected from surveys focused on potential extraterrestrial environments, researchers are increasingly turning to artificial intelligence, or AI. This technology helps them analyze complex datasets more efficiently, isolating patterns and signals that might otherwise be missed in traditional data analysis. One of the crucial tasks AI performs is identifying potential biosignatures. These are indicators of life, such as certain gases in the atmospheres of distant planets that could suggest biological activity. By training machine learning algorithms on existing data from Earth's ecosystems, scientists can equip these systems to recognize similar patterns on other celestial bodies. This not only speeds up the discovery process but also enhances the accuracy of identifying environments that could harbor life. Additionally, AI helps in processing astronomical images and spectroscopic data. For instance, the analysis of light from stars or planets can reveal their chemical compositions. By using AI to scrutinize thousands of spectra, scientists can efficiently identify those that exhibit signs of life-sustaining conditions, such as the presence of water or organic molecules. This automation of data analysis allows researchers to focus on interpretation rather than getting bogged down in manual processing. The implications of utilizing AI in astrobiology are significant. It empowers scientists to tackle large-scale surveys, like those conducted by space missions and telescopes scanning the universe for habitable worlds. As our technology progresses, the partnership between human ingenuity and artificial intelligence opens doors to discoveries once thought to be the domain of science fiction, bringing us one step closer to answering the age-old question: are we alone in the universe? As we gaze into the cosmos, our curiosity leads us to explore potential havens for life beyond our solar system. The search for extraterrestrial life has gained momentum in recent years, fueled by advancements in technology and our understanding of what makes a planet habitable. Among the most promising candidates are exoplanets located in their stars' habitable zones, where conditions might be just right for liquid water, essential for life as we know it. One standout contender is Proxima Centauri b, an exoplanet orbiting our closest stellar neighbor, Proxima Centauri. This planet lies within the habitable zone of its star, allowing for the possibility of temperate conditions. Its proximity, just over 4 light-years away, makes it an appealing target for future observations. Scientists are eager to study its atmosphere for gases that might indicate biological processes. Another exciting area of investigation is the TRAPPIST-1 system, which harbors 7 Earth-sized planets orbiting a cool dwarf star. 3 of these worlds sit comfortably in the habitable zone, raising tantalizing questions about their potential to support life. Observations from space telescopes have already begun to reveal intriguing details about their atmospheres, suggesting that at least one of them could have the right ingredients for living organisms. Beyond individual planets, we have to consider the moons of gas giants, such as Europa, Enceladus, and Titan within our own solar system. Europa, with its icy surface concealing a vast ocean beneath, holds many secrets. Similarly, Enceladus has geysers that eject plumes rich in organics, hinting at the possibility of life lurking in its subsurface ocean. Titan, with its thick atmosphere and lakes of liquid methane, presents a completely different but equally fascinating environment to explore. Each of these locations serves as a reminder that the universe is brimming with potential, waiting for us to delve deeper into its mysteries. The study of biosignatures plays a pivotal role in our quest to understand potential life beyond Earth. Biosignatures are indicators that suggest the presence of life, whether past or present, primarily through the detection of specific chemicals or patterns that can only exist in the presence of living organisms. By analyzing these biosignatures, scientists can glean insights into the environmental conditions that might support life on other planets. For instance, certain gases in an atmosphere like oxygen or methane can signal biological processes, since these gases often interact in ways that would suggest active life forms. The coexistence of oxygen and methane is particularly intriguing because, while oxygen is produced by plants, methane is often generated by microbial life. This synergy suggests a vibrant ecosystem that could thrive in such an environment. By identifying similar chemical signatures in exoplanet atmospheres, scientists create a roadmap of the types of environments that may harbor life. Moreover, studying Earth's biosignatures across different environments allows researchers to establish a baseline. From extreme conditions in hot springs to the frigid expanses under ice, life on Earth adapts to an astounding range of environments. These findings help scientists speculate about where else life could exist in the universe. For example, if life can thrive in extreme heat or cold, then planets with similar conditions might also support life in ways we have yet to fully understand. In addition to searching for specific gases, scientists also analyze geological features and the presence of water, as it is crucial for life as we know it. By connecting these clues with the search for biosignatures, we can better predict what types of planets might be most promising in the hunt for extraterrestrial life. In this way, the study of biosignatures not only illuminates the conditions necessary for life, but inspires deeper inquiries into the mysteries of our universe. Understanding the origins of life on Earth serves as a foundational element in our quest to find life elsewhere in the universe. By studying how life began here, scientists can identify the conditions and processes that may lead to the emergence of life in other environments. This knowledge enables us to develop models and theories about where and how life might exist beyond our planet. For instance, if we uncover that life needs specific chemical compounds or temperature ranges to thrive, we can use that information to guide our exploration. Examining Earth's history provides valuable insights into the different environments that have supported life. From the harsh volcanic lakes to the icy expanses of Antarctica, life has shown incredible resilience and adaptability. This diversity leads scientists to consider a wide range of extraterrestrial settings. Locations like the icy moons of Jupiter and Saturn, or planets with thick atmospheres, may harbor conditions similar to those that allowed life to flourish on our planet. The more we understand our own planet, the better equipped we are to recognize potentially habitable worlds elsewhere. Our research into extremophiles, organisms that thrive in extreme conditions here on Earth, further widens the scope of our search for extraterrestrial life. These resilient life forms demonstrate that life can emerge and exist in environments once thought inhospitable. If life can thrive in sulfuric hot springs or beneath layers of ice, it opens the door to the possibility that life exists in unexpected places throughout the cosmos, perhaps in environments we have yet to consider. Ultimately, learning about the origins of life not only helps refine our strategies for searching for extraterrestrial organisms, but also helps us reflect on the nature of life itself. Understanding our beginnings can deepen our appreciation for the delicate balance that sustains living organisms, leading to existential questions about our place in the universe. In the search for life beyond Earth, we are, in a way, searching for reflections of ourselves.